So, you hear me? Everything's fine? Good. So the last time we started discussing the reduced modeling approach, that is the way that is a kind of traditional way how to enhance computational efficiency by assuming that kinematic field, that is displacement field, is something that is that could be significantly reduced thanks to the special type of information pattern of these structures. So a typical thing, either beam structure or plates and shells. For beam, we said there are two dimensions which are significantly smaller than the third one. The third one being the length, and the two others are placed in the cross-section, particular beam. And then for plates and shell, you're talking about thickness, which is much smaller than the, let's say, mid-plane or in plate or mid-surface in the shell. And for this particular case, we have already discussed how to build, let's say, beam model for the linear theory. And the fact that this could be done either by Euler-Bernoulli type of beam or Timoshenko beam. And Timoshenko having the advantage of having a shear deformation, which Euler-Bernoulli doesn't. Of course, either of these models, either Euler-Bernoulli or Timoshenko, are approximate. And basically, the result cannot never be really the same as like 3D case. But for many of these applications, this does just fine. And on the other hand, it allows you to do a computation much faster. In fact, traditionally, let's say when I started my engineering career, I had a bunch of old engineers who did not use any computer software, but they can do computation with the beam model just about on anything you can imagine. And this is kind of long experience, and they could always stick with a very simplified model. So within 1 year, even that I had access to computer software, then I had my own clients who needed to confirm this, let's say, quickly obtain an approximate result that's obtained by beam model. And then you go into the modeling of all kind of other things, and you really learn how to see kind of building the model in some way. Nowadays, as I said, it's really inverse, and the kind of the sense of my lecture today is really to come up with this reduced modeling approach, which seems to be kind of keeping busy. Many people are quite knowledgeable. They somehow concluded that everything is known in terms of development of this model, and the only thing which remains is really just to get like the most efficient model. I don't subscribe to this approach, but what the hell, you cannot fight everybody, and you have to stay friends with the people and say, okay, this will, if you think that this is everything is known, why not? In any case, this is the step that one has to go. But I believe really that many developments are yet to follow, especially in the spirit of we're trying to couple these different physics, and then basically the traditional domains that shall be collaborating. For example, right now you're trying to build a book which is a thermoelectromagnetism coupled with elasticity and inelasticity and things of this kind. So this really is going to remain for other case and other say course when we had to talk about that. So let's go back to the stuff that some of you are doing. Is as I said, the geometrically nonlinear problem. You have an aspect of large rotation. The last time we talked about large rotation, intrinsically are represented by the orthogonal tensors that could be represented with 3 parameters. These 3 parameters could be either Euler angles or some kind of components of a corresponding skew symmetric tensor, which is brought in connection with this orthogonal tensor by exponential mapping. So develop this closed form formula for exponential mapping as a sum of identity, the theta and theta squared multiplied by these two coefficients. Alternative manner was going through this Euler observation about large rotation and rotation axis being placed in terms of the vector theta. You can write this Rodriguez formula as a identity theta skew, and then the tensor product with these the vectors theta. So and then he said in the computation, the most often used is Quaternion representation, or you can also use incremental rotation that we kind of advocated, in which case you have the best benefits. That is like you have a symmetry with tangent operator, and at the same time you with incremental rotation not being larger than 180 degrees, otherwise you cannot converge. You can certainly obtain quite good results. So once we understand large rotation, we worked out the material picture. That is when you do variation at identity, and then you travel to the deformed configuration, and also spatial picture, that is your first travel by the rotation to the deformed configuration. What is this lambda? Lambda is simply rotation of your cross-section. So if you have large rotation, the cross-section still remains non-deformable. If it was a plane, it will remain the plane, but it's just taken by the large rotation. To simplify in 2D, that we cosine and sine of the angle that you undergo to bring it to the deformed configuration. And then you take variation being a skew-symmetric tensor, which represent infinitesimal rotation. So if you want to mix those, you have to do exponential mapping to bring infinitesimal rotation to the SO3 manifold, and then you do a multiplicative update. So that's the kind of thing that you normally do. But if you take a rotation vector, then you can do update in the tangent plane directly, especially if it's a material configuration here. So this is your theta, which produces lambda, and this is your variation of theta. So you can simply sum them up because they're in the same tangent plane. So you get the perturbed, let's say, variation of this lambda, but simply by adding in the tangent plane theta and delta theta, and then doing exponential mapping. So going through development of these different possibilities, you see there is a connection between the variation of the orthogonal tensor and variation of the rotation vector. So you can go from one expression to another without any difficulty once you understand how to move on. I said that the moving on is allowed by this commutative diagram. That means you can go in any direction, use any parameters you like, as long as you do proper transformation from one parameter to another. So this has been used for a 3D beam. I gave you some results that why is this okay, and let me just very quickly explain how you actually build this type of beam. So we are talking about geometrically exact formulation. It already goes back to the first work of Eric Krasner. Eric Krasner was a mathematician, but very much interested in the engineering problems. He was professor at MIT, so probably he had many good students interested in engineering. So it was certainly of interest to him to look into those problems. And thanks God he did that, because at the end he came up with many original solutions and kind of sufficient rigor of understanding what is the advantage of doing this geometrically exact models. So he has introduced the formulation of space curve beams, and basically worked out how to build these both equilibrium equation and how to build corresponding strain measures. Then there's also notable work of Juan Sivo, who worked out how to use this computation with really rotation. He was benefiting from the paper of Argyris and Reisner, putting it together into computational tool. And actually, it was not only for the straight beams. So actually, then after that came up with when I started looking at that first to get really the type of Reisner type of development for really curvilinear beam, because many of these things are really curvilinear, especially for the shells, of course. So basically, how does it go? Well, this is your beam element. It could be curvilinear, and it's placed in three-dimensional space. So I have a background coordinate system, which is giving me the, let's say, Euclidean type of distances. And I also typically, since I have a curvilinear initial configuration, I have a curvilinear coordinate S, which is parameterizing the length of the beam from 0 to, let's say, uppercase L. And then I have to look into what kind of loading could be applied to this beam. So N bar could be distributed load. It could be in any three different directions. And M bar could be distributed moment. So since you have a beam, you can have not only a distributed loading, but you can have also distributed moments. And then if I want to get an equilibrium equation, what I do, I start with the cutting out the finite part of this beam, and basically I'm setting the part which is the end forces at the section S2, and minus end forces and the section N1, S1, sorry, and then summing up the distributed loading. So this is a vector equation which gives me the linear momentum or force equilibrium equation. Then I can also build the angular momentum, taking moment with respect to the, let's say, the origin of this coordinate system. I can have the moments at the S2 and moments at the end of S1. And I can take the integration of n bar, n phi cross n bar, the contribution of the external load. And I also have to take into account the contribution of n plus and n minus, the internal forces that are liberated by cutting at the section S1 and S2. So when I take all this, I can make a limit process that S2 goes to S1, and you call this S1 to be some kind of a position that you're looking at, and you get a local expression that's derivative with respect to S of these forces, which typically are axial and two shear forces, plus this limited load n bar has to be equal to 0. This looks very similar to what you have with the bar. You have d sigma dx plus b equal to 0. So this is just the stress resultant as opposed to stresses. And then moment equilibrium, which is typical of the beam, which you don't have for 1D truss, basically is like a m prime plus phi cross n prime derivative with respect to s plus phi cross n bar plus n bar. So you can work out this and recognize the equilibrium equation of the forces to kick out this one. And then you're left only with the derivative of m plus phi prime cross n, the vector probability n plus n bar. And so these are your moment equilibrium equations. So once you have these equilibrium equations, you have to ask yourself, okay, what are these stress resultants possible to pair with? And please note that I can establish this equilibrium equation on the exact form of the beam, where S is used as the really curvilinear coordinate that is parameterizing this. And we studied this curvilinear cable element, and we saw how this, using isoparametric elements, how this computation with respect to S, of the derivative with respect to S, could be easily obtained by appealing to the isoparametric interpolation. So Jacobian ds dxi, xi being the natural coordinate, is simply square root of dx dxi squared plus dy dxi dz dxi, where x, y, and z are the components of the particular position vector. And then you take square root of these things and you get your Jacobian. So then it's very easy to go from one space to another. So basically, after we understood how to build the equilibrium equation, the question is raised how actually to get the proper kinematics. So when we study the beam element, we are typically, and this curvilinear beam element, here's this curvilinear coordinate S that is parameterizing the length of the beam from 0 to uppercase L. And we start by positioning local Cartesian frame such that G1 is a tangent vector, and G2 and G3 are perpendicular to G1, and they are placed then in the cross-section plane. So it's easy to obtain G1 as a derivative of the position vector X with respect to S, and you have your G1. And then the other two could be chosen in the way that they are mutually orthogonal and both orthogonal to G1. So you have the notion of a beam, which is given by the position vector, and this unit triad, which is giving you orientation of the cross-section. Namely, G1 is orthogonal to cross-section, and G2 and G3 are in the plane of cross-section. I'm going to consider now the generalization of Timoshenko beam, and in the honor of Rezny, who came up with these papers on formulation, many people call this Rezny beam. So you can now consider that large rotation will bring this cross-section into new position. And basically, the way we are going to parameterize this beam is first of all with the new position vector, x, y, z, phi of x. This is similar to what we have in continuum mechanics, where we have to describe the motion. So every particle which is sitting in the neutral axis of the beam in the initial configuration, x has to be brought to a new position, which is xy, and has to be explained as a function of x, phi of x. And then we also position this, the local Cartesian frame. It's going to transform this frame into a new Cartesian frame in this way that A1 will be again perpendicular to the cross-section in the deformed configuration, and A2, A3 will be placed inside this cross-section. So transforming one orthogonal frame into another orthogonal frame, obviously you need orthogonal tensor. So let's say the space of the variables which are parameterizing kinematics of a beam is basically the displacement vector or position vector, and also orthogonal tensors which are giving the position of the cross-section. So again, we should take into account what the objects are in the initial configuration. They could be expressed with respect to the global frame for the initial configuration, where the unit vectors are called EI, that is E1, E2, and E3. And then let's say unit vectors A are in the deformed configuration, so they could be expressed with the base vectors in the global configuration, which I call E1 phi, E2 phi, E3 phi. But for any practical purposes, we said that these two vectors are chosen to be the same just for the clarity of the concepts. We keep different symbol with the phi, having significance that you are sitting in the different configuration. So basically, this local Cartesian frame, as I said, unit vector brought to unit vector, obviously lambda has to be a orthogonal tensor. Now, if I want to position this initial frame, GI, similar, let's say, a manipulation can be taking place. I have to define lambda 0, where lambda 0 is a orientation of this frame. And you can see, given that the beam is curvilinear, this lambda 0 varies from point to point. But I can just easily compute the derivative of the position vector in any point I'm trying to build this frame and get my G1 and then take a G2, a G3 to be mutually orthogonal and orthogonal to G1. Hence, I have a lambda to be positioning the G basis into A basis. And I have lambda 0, which is positioning the global basis EI into the local basis GI. In many applications of the beam, people develop this in local coordinate system, and then they transform it again into global coordinate system. But if you have a curvilinear beam, it's not so obvious because this local and global coordinate system are kind of changing from point to point. And this is kind of hassle. So one has to work out this for really a curvilinear beam as a transition to curvilinear shells, which are always by the curvilinear. So this was kind of good exercise. If I had a straight beam, this was the work that was done originally by Simon. You just ignore lambda 0. You say this is identity, and you don't worry about that anymore. But we didn't do that here. We actually said, okay, at the end, AI is lambda times GI, and GI being lambda 0 times EI. So this becomes something that we call lambda tilde times EI, sorry. And then basically we have to discuss derivatives and to have variation. Both of these are linear operations. The variation is taking let's say, the virtual field. In this particular case, you're talking about rotation. So virtual field will be infinitesimal rotation that we call delta W. Here we start with this spatial description of the orthogonal tensor. So the kind of proper variation would be you have your variation of delta lambda, which is the one that I was picturing here. Let me go back to this picture here. I'm going first on a lambda. Then I take a variation delta W. So first I multiply by lambda, then I multiply by delta W, or rather exponential delta W, because these guys have to live in the same space. And then I take a derivative with respect to this parameter alpha and so on and so forth. So this way I can obtain for the beam, going back to the expression you just said, that basically the variation of the unit vector AI, which we're going to do eventually, will be variation of lambda times GI. Now variation of GI doesn't exist because this is once for all the unit base that you put in the initial configuration. So initial configuration is unique. Unit base is sitting at a certain point is also unique. So there's no variation on that. So delta GI is equal to 0. So just as we used to a computing variation of the orthogonal tensor. And so orthogonal tensor variation is delta lambda times lambda transpose. And that again times lambda here. So basically these two will give me delta W, the skew symmetric tensor of the infinitesimal rotations superposed at the point lambda in my configuration space, and lambda GI will again give me AI. So I can write this in terms of the axial vector of this skew symmetric tensor delta W, uppercase W, as a delta W lowercase cross product with AI. So this is the way I compute my variation. If I now want to do another linear operation, which is computing derivative, because this one I will also need derivative AI. Now it's a little bit more elaborate because lambda 0 is a function of S. This superposed prime is a derivative with respect to S. So that becomes like a lambda GI all derivative with respect to S. And this becomes basically lambda 0 EI all derivative with respect to S. This derivative should have been outside the parentheses, sorry about that. And now I can say that fixed unit-based vector EI do not change, so their derivative are equal to 0. But I do have these two terms, and it so happens that I can work it out in a way which brings out the skew symmetric tensors. So these skew symmetric tensors are written as either here lambda 0, or sorry, omega 0, which is lambda 0 prime, lambda 0 transposed, or omega, which is lambda prime, lambda transposed. So if I take the summary of all these results, I can obtain that the the derivative of the unit-based vector AI in the form coefficient with respect to coordinate S is equal to this omega plus lambda omega 0 lambda transpose times AI, where omega and omega 0 are corresponding pseudosymmetric tensors, which are defined by taking the derivative of the orthogonal tensor lambda or orthogonal tensor lambda 0 and multiplying with this corresponding tensors transpose. So basically, I can also build this in terms of dactyl vectors, namely, if I have this skew symmetric tensor uppercase omega, I can have a corresponding axial vector lowercase omega. So there will be to this omega, capital omega, little omega, a corresponding axial vector, and capital omega 0 will be little omega 0 corresponding axial vector. So then the same equation is written here in terms of the skew symmetric tensors. I can write here in terms of the axial vectors. And that's about the only complexity you need, and then you just apply this systematically to everything else. In other words, I can say now, if I take a variation of the derivative of AI, this will be the same as the derivative of the variation, so there should be a little delta here, sorry for this mistake. And then basically this will be delta of your, what you just said for the A prime, this is given here, A tilde cross AI, this is here. And the variation was delta W cross AI, so this is actually here, and you take derivative. So you go through this exercise, computing corresponding variations and corresponding derivatives by using the rules that we just explained. And from that one, you conclude that delta W prime cross AI is equal to minus delta W cross omega tilde all cross AI. And then I can also take into account so-called Jacobi's identity about these triple or double vector products, three different ways of writing it, and basically express the last term in this particular way, that this is equal to delta omega tilde minus delta W cross omega tilde, all this cross AI. So comparing what is doing it, what is featuring in the cross product with AI has to be the same vector. Hence, I conclude that delta W prime is the same as delta omega tilde minus delta W cross omega prime. So I'm more in the business, basically, because now I know how to build corresponding variations and for these rotations and corresponding variation, of course, for displacement. So I can now appeal without any fear to the principle of virtual work. And this was basically the idea of Rezne. You first start by using the principle of virtual work, that the work of the internal forces, in this case, normal forces and shears, N, with corresponding virtual strains that you don't know, you're looking for those expressions, plus the work of the moments with respect to the virtual bending strain should equal the work of the external forces, which is the applied force N bar, paired with the virtual displacement, and applies moment N bar paired with a virtual rotation. Then I take a special case where all the fields are sufficiently smooth, so the weak form would recover the strong form. Hence, I can say that M bar and N bar could be expressed by using the equation of the strong form. Recall these are two equilibrium equations that we computed here, that N prime, this is derivative with respect to S, plus N bar is equal to 0, and N prime derivative with respect to S plus V prime cross N plus N bar equal to 0. So from this one, I can express what is N bar and what is from this one M bar, which I've done here. And basically, you can take these results and plug it back into the work of the external forces. Then you compare these two expressions. On one side, you have work of the internal forces. On the other side, you have the work of the external forces, where you introduce the strong form equilibrium equations. So when you work out a little bit this expression, you can compare the final form of this expression down here, and you can then conclude, well, if these two expressions have to be the same, my virtual, let's say, strain that goes in hand with the normal and shear forces is equal to delta phi prime minus delta W cross phi prime. And my virtual bending strain is equal to delta W prime, but we just said that delta W prime is nothing but this guy. So I'm using this identity and writing it here. So with this way, I can obtain, and this was really the work of Reisner, the virtual work expression. Now, this is not what Reisner has done. The next step is really understanding how you actually build these finite rotations. And basically, if you kind of take into account that the finite rotation and the variation have to be built by taking into account the corresponding, let's say, update on the manifold, I can say that given that I have these expressions here, and given that these expressions are corresponding to the object in the spatial deformed configuration, I can then say that taking these results into account, this is basically what I developed here in detail, that you can have like something that book of Mars and Hughes is computing, is asking, calling Lie derivative. That is, you have objects sitting in the deformed configuration. If you were to compute the variation, which is linear operation, first you have to take them back to the initial configuration. This is so-called pullback. So the object you're talking about, those are the strain measures that should be conjugate to the stress resultants, and stress resultants are defined on particular cross-section. A cross-section is taken by the large rotation. So this pullback should be done by the inverse of the large rotation tensor, which is orthogonal tensor, and inverse and the transpose are exactly the same thing. So, and then I take the variation, and I take the result, and I push it forward, transform it back to the deformed configuration, and again, transformation done by orthogonal tensor, which is lambda. So if you compare these two expressions for delta epsilon and delta kappa, it could be quite easily confirmed that this is nothing but pullback, variation, and push forward of the expression which are written here. One is phi prime minus AI, and the other one simply little omega, or derivative of the orthogonal tensor with respect to S. So this way I conclude that basically the finite strain measures for the beam that are conjugate to the stress resultant N and M are given for the forces phi prime minus AI, and for the moments little omega being the axial vector over what you call it orthogonal tensor, that is derivative of lambda times lambda transposed. It actually fits quite the understanding I had before, namely the position vector in the deformed configuration is obtained by phi prime, and the position of the cross section is obtained with the unit vector AI. And because of the shear deformation, these two are not the same. If you had something like well-Bernoulli beam, then phi prime would be the same as the AI, and you would eliminate completely the shear. And then the derivative of the rotation, of course, will be the bending, just like in the Timoshenko beam. The curvature is d theta dx, where theta is the rotation of the cross section. So this is really intuitively, when you linearize, you will get your Timoshenko beam, and intuitively really fits into what you would expect from the finite deformation measure. But this has been obtained by having an idea of Resner that you actually express the first virtual state, and then understanding of how you handle large rotation, how do you handle the objective way of computing the rates with this so-called Lie derivative. We have a push, pull back, and the variation, then push forward. All these ingredients entered into this to kind of get the final result. So when all is said and done, the conclusion is that the strain measures for the finite deformation beam will be epsilon to have phi prime minus A1, and kappa is equal to omega. So now I have everything. I can just have here the proof that I really have a strain measures. So first point is, if I have a rigid body motion of the beam, that means that the new position of the beam is obtained by the rigid body translation. So this is constant vector which takes a beam to a new configuration, and then eventually the rotation that is rotating the cross section of the beam. So this is Q, again, constant tensor times the position vector X. So lambda is just equal to this Q. Hence, I can say A1 is equal to Q times G1 is equal to Q times E1. I started with let's say, horizontal beam, which is aligned with the coordinate axis. And then phi prime is simply the Q is constant, E is constant. Basically, I have something which is canceling and having this equal to 0. And namely, basically, that's A1 and phi prime are computed exactly the same way. They cancel each other. Also, this omega being a derivative and Q being constant, also the bending strain is equal to 0. That means at least the condition, the two expressions that I suggested, if the motion is a rigid body motion, that means large rigid body motion, large translation, and large rotation, I have no deformation. Then these are also the strain measures which are supposed to be objective. In other words, when you're in particular deformed configuration, you already have corresponding deformation. The corresponding deformation are given from the new position vector, which I call phi, and the rotation of the this unit triad GI into the triad AI, which is given by lambda. So now phi and lambda are not constant, but they are measure of the previous deformation. So now on top of this deformed configuration, I superpose the rigid body motion, which is again given by a translation tensor C, vector C, and the rotation tensor Q. These two guys are constant. So then I compute the strain in a deformed configuration. That becomes Q times phi prime minus A1 star. A1 star is nothing but Q times A1. So that becomes Q times phi prime minus AI. So this was your strain in the deformed configuration, characterized by the configuration space of phi and lambda. And this is just transformation of your strain. And that happens to be objective transformation under the superposed rigid body motion. The curvature story is similar. Namely, you have a skew symmetric tensor kappa in this rotated configuration to be a Q times lambda with respect to S times Q times lambda transposed. So playing this transposition, saying that this is your kappa in the deformed configuration, this is transformation of skew symmetric tensor with Q and Q transposed, and corresponding axial vector, little kappa could be simply transposed with Q. Again, you have an objective transformation. So you show two things, that these are indeed strain measures. If the motion is the rigid body motion, there's nothing going on. And if you have a strain measure certain deformed configuration, they transform according to the objective rules, according to this rotation. So everything is fine. So then you can express the components of these vector components epsilon kappa with respect to the triad in the deformed configuration. And you call this little epsilon I and kappa I. And then also the stress resultants you can express with respect to the components in the deformed configuration. And you call these components Ni and Mi. Let's say these components will be the corresponding to the first Euler-Kirchhoff stress type of stress resultants that you can use, okay? Now I can set the constitutive equation with respect to these components. So typical constitutive equation for the simple case is here you have a stiffness for the axial force. This is E, Young's modulus times the cross-section A. Then you have a stiffness for the shear forces. This is a G, the shear modulus times the so-called effective shear section, if you want to take into account some kind of fancy dissolution of the shear stress. And then you have also typical constitutive equation, linear elasticity for the bending. So this is like two bending stiffnesses, E, Young's modulus times E2 and E times E3, where E2 and E3, I2 and I3 are equal to corresponding moment of inertia for the axis 2 and 3, and G being the shear modulus and J being the polar moment. So this is your stiffness for the torsion. Well, I can then write this also as a in the tensor notation or vector notation to be n equal to lambda tilde Cn being this 3 by 3, let's say, matrix times lambda transpose times epsilon, and then would be lambda tilde Cn lambda transpose kappa. So this way I can complete the whole development, building a total potential energy of this beam, where the energy internal force is written as 1/2 epsilon dot n and kappa dot n. And so I put what these strain measures are. I put my constitutive equation and basically write it this way. So this is simply like quadratic form in the terms of these axial strain measures and then bending strain measures, axial and shear. So now I can also do the, let's say, rotated version of these things. Then I'm pulling it into the initial configuration. And these are now uppercase letters. So this pulling it back is sort of similar to second Euler-Kirchhoff stress, but the pullback is only with rotation. So you recover something towards Biot stress. Only rotation is actually used. So to have a physical interpretation of these stress resultants, I have to look a little bit in 3D developments of the theory. So I have a position vector of any point of the beam inside the cross-section in the initial configuration. This is equal to the position vector of the neutral axis plus xi I being for 2 or 3 multiplied by the corresponding unit vector gi. That maps into the new position vector, which is phi of x, plus the same xi I, because there's no change of thickness, times the corresponding new position of these vectors g2, g3, which is now called a2 and a3. Then I can obtain my deformation gradient by computing the with respect to the 3 coordinates, s and the 2 coordinates in cross-section. And basically, I can work out the variation of this deformation gradient. I can take a corresponding stress vector to be P1 and P2 that I obtained as a product between a first pillar critical stress and the corresponding base G1. And here the first pillar critical stress corresponding base vector G2, and P3 is the first pillar critical stress and the base vector G3. Hence, I can write my let's say a spectral representation of my first pillar critical stress as this vector P1 to 0 G1, and then P2 to 0 G2, and P3 to 0 G3. With these components that could be expressed in terms of the base vectors in the deformed configuration. So now I enter into this development of the internal forces. I start pairing the first pillar critical stress and the variation of deformation gradient that is written this way. I also introduce the moment equilibrium equation, which for the first pillar critical stress reduces to saying the PF transpose is equal to FP transpose, or skew part of PF transpose is equal to 0. That gives me this type of equation and allows me to express what this part is, which I can then use in this upper expression. And then going through this development, I can lose the internal forces to this guy and to this guy. So I can recognize this is variation of my axial and shear strains, and this is corresponding stress resultants. So obviously, it turns out that stress resultants are the resultant of the first pillar critical stress for this particular beam. And here, this is variation of your bending strain, and this here are these bending moments, and of course, torsional moment, and they are resultant again of the first pillar critical stress. So this would be like a spatial formulation of this theory. I can also do the material representation. So here it's in the conclusion. First, I stated if you do a spatial formulation, here's the way in the conclusion, the virtual work is written as a Lie derivative of your true strain measure, which is written as V prime minus A1, scalar product with the stress resultant of axial and shear forces, and then Lie derivative of your bending strain measure, which is little omega. This is a derivative of your orthogonal tensor lambda with respect to S, and then turn this into an axial vector, the scalar product with the bending moment and the torsion moment. And the constant equation for n and n could be expressed with this quadratic form as lambda tilde C n lambda transpose and lambda tilde C n lambda transpose. You can do linearization. Again, linearization is similar to computing the rates. Only this time around, instead of a lowercase delta, you use uppercase delta. That means you're looking into an incremental displacement and incremental rotation. And basically, you get the two contributions of the tangent operator, one being geometric, where you take a derivative of a virtual strain, which still depends on lambda, basically. And that's why you have this contribution. And then you have let's say, the derivative of the virtual strain in terms of bending. And then the second part would be material part. We have this contribution from a virtual strain and the incremental strain, virtual strain, incremental strain, both for the axial and shear actions and the bending. If I now take the finite element interpolation, I can take isoparametric elements with any number of nodes. I think it was developed there for 2 nodes and 3 nodes, because 3 nodes make sense if you want to represent a curvilinear beam. And then basically you have your representation of variation increments using the same shape functions. And then you can present your linearized expression that means the internal force vector and the part of stiffness unit, which is material, and with geometric, and that amounts to that. So basically you can see that in reality, the true identification of a stiffness matrix, this material part is symmetric, but geometric part is not necessarily symmetric. And then if you really want to get true quadratic convergence, you have to keep it non-symmetric. That means the number of operations when you're solving the system is doubling. And you can try to symmetrize, but then you lose quadratic convergence property. So how do you deal with this? Normally, you deal with using quaternions. In other words, you actually never really push computation in terms of diagonal matrix. You rather push computation in terms of quaternion. Namely, if you have existing rotation, it's represented in terms of quaternions, which you call the, let's say, Q and Q0. And then you compute the infinitesimal rotation or infinitesimal increment. That this is about update at each particular iteration. So imagine you compute a small rotation at increment I. This is uppercase delta times W, discrete metric tensor. Then you bring it into exponential mapping, and you multiply from the right-hand side to lambda I, because first lambda I happened, and then you have this increment. And this way you get lambda I plus 1. So how do you get the corresponding quaternion from this one? Well, basically, this will give you simply taking cosine of delta W over 2, where delta W is the norm of this vector delta W. And the vector part will be sine of delta W over 2 divided by this norm, and then multiplied by this vector here. So the corresponding orthogonal matrix of this guy is here when you need it, and corresponding update is again done in terms of the quaternion. This allows you also to build the update to the curvature in terms of the incremental rotation, and that has been worked out. In the process, you obtain this operator T, which we already obtained when we are doing this commutative diagram of different ways of parameterizing large rotations. So this is the same type of operator T. In any case, there's also kind of subtle developments, but when all is said and done, you have miraculously perfect version of the beam, which is working quite well in a very robust way. Some things should be said about the locking phenomena, and maybe it's easier to illustrate this in a two-dimensional beam. So here are some of these references that relate to different developments. So there's again, first version of 2D with the curvilinear beam was done by Reisner with the same idea of using the strong form of equilibrium equation to identify virtual strains. There's also an interesting paper by Antman, who also wrote a book on that. Not easy reading, but still a structural mechanics book. And then there was an implementation of Seymour, Hempstead, and Taylor on a beam with a kind of shear. And then we've done this paper to kind of demystify different locking phenomena. So this is your beam in the initial configuration with the cross section and the neutral axis, and you have orientation of your local frame, but some kind of angle alpha. And then you have a deformed configuration, so you have a large rotation in the angle psi. So your configuration space is two coordinates of a displacement along x and y axis, along E1 and E2, and then your rotation psi. So your lambda is a cosine psi minus sine psi cosine psi. Your lambda 0 is cosine alpha minus sine alpha cosine alpha. So if you multiply lambda 0, it simply amounts to adding these two rotation angles because they're all taking place in the same plane. Then your axial strain and shear strain could be obtained by dotting the final result with the A1, A2. So E becomes A1 dot phi prime minus 1, and gamma becomes A2 dot phi prime. Since I can write phi prime as the E plus 1 times A1 plus gamma times E2. And then curvature becomes simply the derivative of psi. This is just like a Timoshenko beam only with respect to the curvilinear coordinate. This is d psi ds. If I make it, let's say, a two-node beam, I'm taking isoperimetric mapping. In respect to this real beam, I'm taking a beam placed in the isoperimetric coordinate space, where psi varies from -1 to +1. So these shape functions are built in terms of psi, and I get 1/2 minus psi, 1/2 1 plus psi. Then ds dxi, which is Jacobian, is dx dxi squared plus dy dxi squared. This is x2 minus x1, y2 minus y1, all square root of that. That becomes basically L divided by 2. It's the length of the element divided 2. So the computational derivative with respect to S is very easy. It's computational derivative with respect to psi, where everything is defined in terms of psi because you're talking about isoperimetric interpolation. And then you take the result and multiply by 2 over L, where L is the length of this beam, and beam could be any orientation, including the space, not necessarily along any of these axes. And then I take the isoperimetric interpolation for displacement U and V along X and Y axis. and rotation psi. So if I go through these developments, then I can build my exact expression for the bending strain, axial strain, and shear strain. You can see this guy is linear, but these guys are heavily nonlinear because cosine and sine are, of course, a nonlinear function independent of psi. Now, this is a little bit less obvious when you look at such a long expression. But again, recall, we talked about the last time that you have a locking phenomena, inability of simple Timoshenko beam element to represent the pure bending, and you have only two node element. So the same problem comes here. If you want to represent pure bending in this particular case, you have to have something which has a zero shear for any value of psi. So zero shear for any value of psi, given that psi varies and multiplies this psi 2 minus psi 1, the only way you can make sure that this doesn't occur is if you really put this one psi 2 minus psi 1 equal to 0. But if you do that, you're also killing the interpolation for bending. And here, if you have a curvilinear beam, it's not only a question of a shear locking, just like in the Timoshenko beam element, it is also a question of so-called membrane locking, the same type of phenomena. If you want to have a, let's say, a zero membrane strain, you have to kill the terms that are multiplying psi, and they again psi 2 minus psi 1. Again, they lead to a kappa equal to 0. So how to cure this locking phenomena? The simplest case was that we discussed this yesterday. Just take a single Gauss point. That means your Gauss point is at psi equal to 0, so everything with psi will kick out, and the weighting factor is equal to 2, and you're done. So basically, in this beam element, you can certainly do this reduced integration, what is called one Gauss point. For shells in place, you can no longer do that because you have a zero energy mode. So there are lots of developments, people developing shells, they are using this reduced integration, then they had some kind of stabilization and stuff like that. So early version of this software done at 3D, they had a lot of that. And even now in some codes, because these were codes which are fairly open and not very expensive, so many people bought these codes from Berkeley, from Livermore and stuff like that. And I would say many commercial software were using it and turning it into like a commercial affair. And then even today you have kind of in many software some of these a little bit shady elements which are plagued and have a really not very good behavior. So one has to be careful in developing all these things. Anyway, when you now all done and you get the proper implementation, so this was one example that he said you can handle in a single shot, and you get really perfect match with the because basically for geometric exact beam it's a very simple problem. Here the moment is constant, bending stiffness if chosen constant, then you really have like a linear rotation, and in your interpolation you do have linear rotation, and the curvature is equal to constant. So basically, in each computation, you need just two iterations. First, to go to the phone configuration. Second, to recognize that you're right place, and poof, that's it. But so you can try it with your software if you can produce this type of thing. Then there was also computation of this instability. This is a famous paper where we had some kind of closed analytical solution published in this paper. So basically, there's like a circular arc, but with not symmetric boundary condition. On one side, it's a simple support with the hinge, and the other side is built in. And then you press it with the force in the middle. So here it was a given force displacement diagram for horizontal and for the vertical displacement. And basically, this is the deformed configuration when you have an instability. So you can see the displacement could be quite big. In fact, if you go back, they are the order of 100, and the radius of this guy is 100 basically. So you really like you squish the frame. It's actually obvious here in the critical point. And so one lesson that we learned, if you now take into account a better representation of the curvilinear geometry in the initial configuration, which is the case with 3 node elements, here you take the same number of nodes, 42 node elements or 23 node elements, obviously have the same number of 41 nodes. 2 of them are blocked with a boundary condition, one being built in, the other one being simple support. So solving the same number of equations, but here you're getting almost exact result. Well, it's not so bad either, but this one is even better because you have a better representation of the curvilinear geometry, which is spherical in this particular case. And there's a paper by Argyris that has brought this lateral buckling of angular frame. Basically, what you're doing here, you put angular frame on two super support. There's a symmetry here, and you start turning these supports. And so, what's funny, you need some kind of perturbation, but the frame will move out of the plane, and then basically you start having this lateral deflection, and you go all the way around. So basically, these are like a side view with the lateral deflection. The certain part you snap out, and you start going. You're turning these supports, but it's going like a full circle. So this is now a plane view, and so on and so forth. So once you did the statics, you can have ambition to go to dynamics. So if I do have a Lagrangian formulation where this coordinate S is used on the initial configuration, adding dynamics is not so laborious. I can simply have an initial term that I have. So I have a, let's say, a linear momentum that is simply the mass density times the cross section. So I call this A index rho times velocity. And I have angular momentum, which is the moment of inertia lambda transpose times W, where V is velocity and W is angular velocity. Hence, I can say that the kinetic energy can be written as a quadratic form, which is 1/2 V dot A rho V and Psi dot I rho Psi, where this Psi is on the transpose W, where now bring it back to a initial configuration or the material representation of this. Hence, if I have my internal energy written this way, I can then conclude that in dynamics of this case, I can count with the Hamiltonian to be a sum of the kinetic energy, a potential energy. And if I apply no external force, just initial condition to start the motion, this Hamiltonian should be conserved because total energy in this motion should be conserved. So my implementation should be capable of preserving this energy, and you can have the best performance of the scheme running over a long time. In fact, we can show easily that you can actually preserve this energy. You can also preserve the linear momentum. These are kind of developments that I saw there. You can preserve the angular momentum, and you can finally preserve the total energy. So this formulation has certainly features that are quite desirable, giving you very high quality of the results. Once you go suffering, developing all these equations, please, it's not for nothing. There's no approximation, you get that correctly. So if I want now to do this entire integration scheme, basically I'm doing a one-step scheme. We talked about these two basic schemes, which is the implicit and explicit Newton type of Newmark's type of method. The implicit was a trapezoidal rule with its coefficients beta 1/4 and gamma 1/2. And central difference was explicit with the gamma again equal 1/2 to be second order scheme, but beta equal to 0. So whichever is the version I'm using, I'm now discretizing everything from Tn to Tn plus 1. And I know the value of the configuration space, which is the displacement, the rotation, and the derivatives, V and W. And I'm asking to obtain all these values at time n plus 1, such that the equations of motion are verified. Here, for example, we use a midpoint scheme to be implemented n plus 1/2. So we can show that discrete approximation, this type of scheme can enforce the conservation of linear momentum. That also can enforce the conservation of the angular momentum. And then we have a corresponding updates that are worked out here in detail, and basically something called the Cayley transformation to get corresponding update of the rotation. That's the only complexity. There's really no point of going into this detail because there's just lots of details, but it comes down to things that we already discussed and just more laborious. And then the trick is, if you now want to make a energy conserving, and you're running this with the midpoint scheme, where this is computed, the variation at 10.1/2, you have to leave this, the constitutive, the stress resultant N and M, or in the material representation, uppercase N and uppercase M, without any index, because you're going to be using something called algorithmic constitutive equation. So this algorithmic constitutive equation, they have to be such that the energy is preserved. And so it happens that this can be enforced if N is computed as an average of En and En plus 1 multiplied by the Cn tensor, which is for the axial forces and the shear. and M is computed as the average of the curvatures at kappa n and kappa n plus 1, multiplied by the constitutive tensor for bending and the torsional moment. Now, this is not your midpoint formula. This is more like trapezoidal rule. So if it turns out like a virtual strain are done by midpoint, and the real strain, real stresses are by trapezoidal rule, and combination of those two then preserve the energy. So this is your energy conserving scheme. And you can then run for a long time, infinitely, and basically you're going to be preserving energy all the time if you didn't put any external force. So it gives you a very robust computation of this type of thing. Now, the problem is if you have a very coarse mesh, if for some reason you incite the high frequencies, if you really want to have a good representation of high frequencies, you have to have a very fine mesh. If you don't have it, then the high frequencies are not resolved, and they end up giving you lots of numerical noise, especially if you don't have damping. You cannot get rid of that, but even if you put damping, you kind of kill not only those modes, but you kill everything else, and then again, it's not very good. So the idea was to develop something called energy decaying scheme, where on top of the energy conserving scheme, you put corresponding enhancement of this algorithmic constitutive equation, so the higher order modes are removed. And this enhancement goes as follows. This first part is enforcing the energy conserving. If you take a trapezoidal loop type of evaluation of axial and shear forces and the bending and the torsional moments. And now the second part is some kind of coefficient alpha multiplied by C, the elasticity tensor for axial and shear forces, and the difference between En and En plus 1, where these are successive values of these axial and shear strains. And the same thing is done for bending. You take this coefficient alpha times the constitutive tensor for bending and torsion, and then successive values kappa n plus 1 minus kappa n with the strain measures for the bending and the torsion. The rationale for that is basically if you have high order frequencies, as opposed to low order frequencies, the time step is for low order frequencies, you have a very large, very small value of omega, and very large value of tau or period t, because it's 2 pi over omega. Omega being small, the corresponding period is very large. So the time step for a kind of fundamental mode could be typically just a fraction of the mode. And basically you will have a very small correction to En minus En plus 1. On the other hand, if you have high frequency, this is like a very large value of omega. And so 2 pi divided by large value will be small value. So for a high frequency where you have a small period, the difference of these two could be quite significant. And what you're doing with this, you're basically taking it out. You can show that if you go to development, what is incremental energy, you can see you have the part conserving energy, and then you have a part which is the one which is quantifying decay from these quadratic terms multiplied by the corresponding factor alpha. And so this way you're always pumping out the energy which is produced this high frequency mode, simply because of the coarse mesh, you don't have proper resolution of this high frequency mode, so the result will be just pollution. And that's actually what we do here. So basically then you can have modification of the scheme, how to compute the incremental displacement, incremental rotation, velocity and angular velocity and so on and so forth, and how to get this under control and how to do the computation. So here's your one of the really well-known benchmarks about this thing that I discussed. There's two rigid links in this one, and then you hit it, and then basically you're producing your different motion, and at a certain point when it starts turning up, and then basically the different energy decaying scheme, you can play with different values alpha, and much energy you want to take out, you can take, but setting out the proper coefficient here. So it's always has to be done with the care when you're kind of mixing the real dissipation like plasticity damage or something like that, and this numerical dissipation, which is controlling the high energy mode. But basically you really need this to be controlled. You see with different alpha, a very small alpha will give you this pollution of the results with a spurious oscillation, because high frequency modes are there, they're not killed all. But in the biggest alpha, you have always a very nice type of transition, and you don't have a pollution whatsoever. This is spinning over beam, so you can have some kind of energy conserving or energy dissipating scheme type of results, and so on and so forth. So this is the kind of short conclusion that I try to give you the presentation of a large displacement type of thing with the beam elements. And the main difficulty was a non-vectorial character of large rotation. So we learned that you can present that either by orthogonal tensor and then two variation of orthogonal tensor in the material spatial configuration are corresponding symmetric tensors that could be represented that we call the psi and w, and you can, or delta psi, delta w rather, and then you can represent that with the axial vectors, and then you can also do like a vector-like parameterization of this rotation and using this commutative diagram reduced to a simple form where you have a symmetry with tangent operate. Then we worked out this in terms of proper implementation, trying to avoid the locking phenomenon. That is, you need like either reduced integration or something of this kind. And then basically the dynamics with a better integration modes like energy, better integration schemes like energy concerning energy decaying. So that gives you kind of everything that you wanted to do in the beam. I'm not sure I want to do the shells. Maybe just one picture up. Share screen. Basically, the shells, it's quite laborious, and there's interest to develop these shells. But there's just one thing that I want to, and then you start with this spatial configuration. These are resultant of the first field kick of stress. Only have now two, is one direction, two directions, so on and so forth. And you have to deal, how to deal with this computation of Christoffel symbols. Well, you can do that by using really the computation with the local coordinates. Especially this is the key idea. I think I asked you this small exercise. If you didn't do it, here's the way I do it. So you have here a global Euclidean frame, here a local frame, G1, G2. And then you can go transformation of this and to that one is just orthogonal tensor because this is positioning a global frame E1, E2, E3 to global frame G1, G2, G3, and both of them are orthogonal. This one I'm looking for, but this one I can obtain easily because I can build as a parametric representation of my shell element. I bring it down to psi eta plane, flatten it up, and X is directly interpolated with the natural coordinate system. So I can obtain this transformation very easily. So combining this to transformation, I get the transformation that I want. And that's basically what is done here. So this is the first transformation with respect to X and Xi. This is the second between X and S, orthogonal tensor. And then combining these two, basically I have this transformation to obtain the derivative with respect to S1 and S2 if I have derivative with respect to Xi and eta. As simple as that. So this is done systematically in each and every Gauss point where I need computation. I never really need to have any kind of curvilinear coordinates. It's just local Cartesian coordinates and the life becomes very simple. I can deal with locking phenomena and so on and so forth. So basically the idea is that now these are variation, very similar pictures we've done is just pushing it to shells. I wrote a series of papers, so but the key point I want to say is this one. You can have now the membrane deformation for the kind of shell I'm advocating, and shear deformation, and finally bending deformation. Again, you see that these are generalization of what we just done in detail for a beam. This is the rate of your rotation tensor. This is the positioning I vectors into the deformed configuration where one, let's say, is perpendicular, not perpendicular to the shell, but goes along the fiber. And basically, the key point, this is not the same as the classical work on shell theory. You have books on Green Zedna, which is one reference, and then there's this one of these handbook, the physics books, Nagdi. So actually, they do membrane deformations, the difference between first fundamental form, and bending deformation difference between second fundamental form. You see, they are not the same. In fact, you can compare what's the difference in the type of shell theory that we've done here. We are actually using proposed shell theory is actually done with the proper type of lambda transpose time F, whereas these guys are doing this deformation gradient type of thing where these vectors are phi comma alpha, as opposed to these vectors being A alpha. So this is not the same type of strain measure. So if you compare this with the 3D elasticity, where this being deformation gradient, the classical shell theory is more like using Green-Lagrange strain, whereas this proposed shell theory is using something like Biot strain. And that actually you can do it there. Then you linearize and you can get some really very good behavior, handling large rotation, getting rid of the locking. And then what the hell you have a kind of nice results. We can mix the plates and stuff. And this is also worthy when you now linearize. There was a thing that we are doing There was a well-known work of Magyar, where he did the shallow shell theory for Kirchhoff-Lab type of theory. We have no shear, and he linearized the configuration to be a shallow. Then you can do local approximation of this. Now, when they extended this to a shear deformable, because this was the better to build the fine translation, both Belichko and Christensen made a mistake, coupling membrane strain not with a rotation, but with a type of derivative displacement. Well, if you have a shear deformable, basically it's like the same thing, because theta would be U3, alpha, but in this one is not. So the idea is really, since we were able to correct that, you can build the perfect element, because you first choose what you need for rotation, then you have one set of enhancement to take care of the shear locking, and another set of enhancement to take care of the membrane locking. So we build something like a four-node element of this type of, basically it's like a shallow shell element. So, and you have a projected plane of this element, which is cutting into middle of each side. And basically first you build the approximation, this projected plane, and then you put it into global coordinate system. So this element is doing a perfect job in many different applications, really competing against end of the line DKQ, but contrary to DKQ, discrete Kirchhoff quadrilateral, you can get into account shear, and DKQ cannot. This is hybrid stress interpolation again, and this is even now node element, this reduced integration and stabilization. So the result is a membrane dominated. This is pinch cylinder. It does again to converging to 100 degrees. It's like 100, let's say, which one is a little bit too flexible with the hybrid stress. And now if you have a pinch cylinder with the end diaphragm, now the results are not so good, because you don't go to 100%, but if you now play with the mesh, because basically what happens here when you have that diaphragm, the deformation is very localized around the point here. So you kept the same number of elements, but just put a dense mesh close to the force and more coarse elements, large elements far away, and you can go down to 100%. They just assume that basically you need a mesh refinement, and we did this for shells. After that, there was a thesis. Uroš Bohinc, we were doing model adaptivity for different plates and stuff like that. So this is really what I said, when you adapt the mesh, you're again on really perfect in that sense. And this is almost the best results. Spherical shell with the hole, you go to 100%, as opposed to other guys, DKQ, DKT, and this is without hole. You can get, again, this one proof, as opposed to other guys converging a little bit more slowly and stuff like that. Twisted beam was the reason I was hired at EPFL, because they tried it before. They failed miserably. The shell element called jet. These are different repairing that we built this element that was all correct and stuff like that. So this is the stuff that I wanted to present here. Now, let me maybe try to complete this. We also had what the hell is that? If there's lecture, this one, multibody. Okay. So when I have a mastered application of different type of models for structures, I can also go and I can also go to do what is called the multibody dynamics. So basically, in many of these applications in airspace mechanical engineering, you have to have moving parts where many structures are put together with different connections, and they keep turning. That's the case of engine, whatever the landing gears, antennas, and so on and so forth. So we talk about multi-body systems. So historically, this multi-body system was studied by a very large community. The leader of this community was in Germany, Professor Schielen, and some time ago, when I was soon after I arrived to Kashan, we organized a nice meeting where he brought all Germans, and I brought many colleagues from France, and we had a very nice meeting in flexible material dynamics. But the big deal was the flexibility. Before that, they were assuming that the components of this multi-body system were rigid, and they could be represented with the sort of modes that are basic modes, and all the flexibility was concentrated in the joints. Now the problem that the parts of these machines are becoming more and more slender because you have a very high resistance composite materials. So the deformation becomes larger, and also the operating speed is getting larger. So with the operating speed and high inertial effects, again, deformation becomes important. So wherever they try to adapt this software that was built with the rigid type of components to a flexible components, it really didn't work out. And so there was a really large opening at that time to build lots of these flexible multi-body systems. And at the time I studied a lot, something like a robot arm, because the ideal of the robot at that time was to human body, and you have to kind of reproduce the behavior of the human body, and the deformation, the control, and whatnot. And then sometime down the road, they turned this ideal of the robot into like insects. So there was became notion system of system, and then it became much less appealing to study what the hell insects are doing as opposed to what human body is doing. Then I switched to other domains or whatever. But this is the type of thing that we presented some time ago in this conference in Milan. So basically the idea goes as follows. We were studying this flexible multi-body dynamics, and we really wanted to get all the power of the finite element modeling and be able to run this for a long time. So the idea is that, as I just said, that the multi-body system now appear in a number of applications in automotive industry, in machinery, like something like transmission or airspace antennas, landing gears, and then biomechanical skeletons, and so on and so forth. And then traditional approaches were the codes that are well known at that time, Adams, dots, where they basically had a collection of the rigid bodies or very low number of nodes representing deformation, and then all the action was concentrated in the joints. And then they try to run this in a way. But if you really take into account flexibility, then representation by rigid body is far from being sufficient. So one has to revisit everything, how you build this formulation and theoretical formulation, discretization of your flexible multi-body system, and how you actually do the computation for something like something called partition solution procedure and so on and so forth. It's large. So basically, this is what I wanted to cover, like formulation, then time integration, computation approach in the operator split. So at that time, we just came up with a French version of my book that I advocated here in English, but you have it in French if you're more comfortable. And basically, the idea is that typically you can start with the solid body as the model, and I'm representing the flexible component with the solid body. And basically, if I take something like a green Lagrange strain, this would be like 1/2 u square minus identity. And my second pure Kirchhoff would be something like a derivative of the internal energy with respect to the green Lagrange strain. And if I had some Van Kirchhoff material as the simplest one, hoping that I never run into very large compressive stress and large compressive strain, I'm fine with that. Then becomes just a linear equation that is L60 tensor times green Lagrange strain. What is characterizing this type of formulation? I can set dynamics in the inertial frame that is fixed coordinate system, and I have a very simple expression for the kinetic energy, which is quadratic form in terms of velocity dot density rho and velocity integrated over domain omega times 1/2. And basically, this is my set of equation. I have a linear inertial term, mass times acceleration, plus the internal force, which could be nonlinear because I have large rotation, large deformation. I could have inelastic behavior, anything you want, equal to the last forces. And what is characterizing this approach with 3D solids, I can impose, if I have no external forces, energy conservation. So Hamiltonian, which is internal plus kinetic energy, remains constant. Now, if I go to the beam, we just discussed this in detail. I have my let's say for some reason, very slender component. So more appropriate model would be a beam. So I can have my deformation measure for the axial shear strain, my deformation measure for bending and torsion. I have my constrictor models to be, again, simple ones. And basically, I can obtain my kinetic energy, again, as a quadratic form. And the linear inertial term would be mass times acceleration. Internal forces could be a function, and only a function of this rotation, typically they are equal to the force. And again, if I remove the external force, what characterizes this model is that the total energy, Hamiltonian internal plus kinetic energy, is conserved. So basically, whatever is the model I'm using, either solids or beams, the problem that I have to solve is the following. I'm using the time integration scheme. I know all the values of displacements, velocities, eventually rotation if I have a beam, and angular rotation, and I now try to find the values at n plus 1. So I can use any type of time integration scheme here, particularly midpoint scheme with alpha equal to 1/2. And I'm computing these values here either for solids or for the beams. And I can enforce with the constitutive model the energy conserving or energy decaying scheme. That's what we discuss in detail. So basically, I'm just connecting this thing. Here's the illustration. What does it mean when it's energy? So this is Bosch, for example, when it starts swinging to the left. At a certain point, you hit this one and it starts vibrating because this component wins. It keeps going up. The other one has to turn around, and you have a axial shock in this one. So you see, if you have energy conserving, you can see it start swaying, and after it keeps vibrating like crazy, and then this vibration will kill the motion. So you cannot carry on. You can look at it again. This one started there smooth, and then after boop, 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 it never really stops. And actually, at the end, it had difficulty. When if I have decaying to take out this high frequency, you see, poof, it turns out after it comes down, it keeps going without any difficulty. You see, so that one really becomes more robust because you remove the troublemaker, which has like a high frequency, and they are not there, so they cannot really trouble your computation. So you can turn as much as you want. There's no problem. So this is the type of thing. This is the moment when this component wins at 0.64. If you have energy conserving scheme, you're going to still be conserving energy. If you have this high frequency dissipation, you take out this energy, and your stress will be better profile than the one which is governed by some kind of numerical noise that you not really control fully. So now, what really characterizes this multi-body systems as opposed to just beams and solids is the joints. So the most often I use the holonomic joints, the holonomic constraints. So basically, here's like illustration of so-called revolute joint, where basically these two components are joined in a way which forces the two components to move two ends that are connected in the same way, namely you have component 1 and component 2. The displacement of component 1 and the displacement of component 2 at this joint where they're connected has to be the same. And also the relative rotation could be different only around this axis that you have for the revolute joint, and two other rotations have to be the same. So I can say that the one way of handling this constraint would be in terms of Lagrange multipliers. So here I will have this Lagrange multiplier enforcing the equivalence of 3 displacement components. So I'll need 3 Lagrange multipliers hiding in lambda. And then I have another one for the rotation and second one for rotation. So altogether I have 5 Lagrange multipliers. And in fact, if I'm handling revolute joint, the only thing I care about that there's actually 2 different rotations in this axis T3, but other than that, around axis T3, but other than that, everything else has to be the same. So, okay, if I first start computing this by using method of Lagrange multiplier, I have to do computation for the first component, second component, and then also bring all these 5 Lagrange multipliers for each time I put a revolute joint. Of course, that's a lot of computation. That's the one that you can do. And basically, the idea that we used was this coupling the software, that you take a software for one component, software for another component, and you simply couple them in terms of these joints. And then you have like operator splitting, how you actually split this up computation, where you handle this joint in order to keep this computation stable. The same ideas were used not only for multi-body dynamics, but they were used for fluid structure interaction problems. And as we go along, I can maybe show you that if you're interested, but none of you is really into fluids. So basically, there was really like, one component is computed by one model, could be solid mechanics, and the other one is by model 2, which is structure mechanics. And then all of them are communicating with the same interface. So these lambdas are just local Lagrange multiplier that are connected to this, and that's actually how we do computation. So if you want to take into account when is it stable or not, you have to enforce that this type of criteria is verified, that you always have it less than equal to 1. And basically, you're typically coming down to the conclusion that more massive structure should be moving first, and then the less massive structure should be going after. So this is really the idea of this localized Lagrange multiplier. Basically, here, when you have these two components together, and let's say they have the same horizontal displacement, you can say that u2 of this one and u1 of that one times lambda 1, 2 is equal to 0. So that gives me a global equation. Or I can introduce some kind of node which is sitting down in the middle, and the only one occurs. This is this intermediate surface. Then I can connect 1 to this intermediate node. This is local multiply lambda 1. And 2 to this intermediate node. This is local multiply lambda 2. Now these two guys are not the same guys, and I have two equations. Although I have more equations, now I can split the problem. And I can do this operator splitting also when I'm doing the solution. And it's basically the coloring of how we actually done this and how to keep it stable. Again, the most massive is going on and so on and so forth. So you can, that with conservative, you can do the dissipative scheme. And I think this is the one when you have it in this, what you call it, the split type of solution, and you can go on. And you can kind of reduce the number of iteration if you go through that and so on and so forth. Now, this was done when you have Lagrange multipliers. And as I said, here's the whole list of constraints for different type of holonomic constraints that are corresponding to different joints that you find in typical multi-body system. So you have a simple spherical. This is your wrist, that basically between your hand and your bone on your arm, you have connection which can go in any direction rotation, but the displacements are always the same. So that's precisely the spherical connection. You only need 3 Lagrange multipliers enforcing displacement in 3 different directions. Then you have this prismatic revolute I just described. There's only one rotation which is not the same. Then with prismatic, that amounts to saying you have like something like a square going around the square. So this way you can control this, let's say, displacement in some way, but you can only slide in one direction, and all the rotations have to be the same. Then you have planar and whatnot. But we also did a little bit different approach with one of my students. We implemented so-called the relative motion approach, where actually on top of your beam, you add ability to handle a local equation. So for example, if you talk about a spherical equation, you already enforce that all displacements are the same. You can only have the 3 components of relative rotation. So you can have like a one node to be a master, the other one to be slave, and the motion of the slave is expressed with the global motion of the master plus the 3 relative rotation. If you have a relative joint, this really pays off, because what you need the motion component of the master node, and basically simply a single rotation to get the slave node. Then prismatic, you need a single translation to get the slave node, and so on and so forth. So that also was implemented. And then finally, we dealt with the non-holonomic constraint. This is typically like, if you have something like a sliding or friction or turning into the plane, in which case you have to kind of deal with getting like velocity constraint, or like something that is changing. And basically this is also that we managed to handle. So this was the kind of message of this multi-body system. Basically the main novelty is that you have to deal with these different constraints. And the way you can do it is either through Lagrange multipliers or through this relative motion, and one or the other that kind of be worked out. So if you're interested, I can give you the books of this kind. Okay, it took a little bit 5 minutes more, but what the hell? Do you have any questions or comments before we take a 15-minute break? Tout va bien? Everybody is not too tired? At least you hear me, huh? Say yes.
That's right.
Okay,
Yes.
so any question, any comments, or too quickly? Well, yeah.
Just one little thing. When you were explaining the Bing model, and I don't know if I got it right. What you said that when building the model, in terms of the first Kirchhoff stress strength, that this model was in a spatial description.
Yeah. Right. Yeah. Basically, the idea is that if I do this, share screen. If I take this. Unfortunately, that's not. I got the wrong file. Sorry. Where's my structure, knowledge. Beam, okay. No. Just to get the right page. Maybe this could be like a good illustration. You see, this is my configuration space for the beam. It could be also for the shell. What is actually configuration space? I have a position vector or displacement, and I have a rotation of the cross section. So this configuration space, which is more difficult to handle, this is this SO3 manifold which handles large rotation. Okay. So in the initial configuration, I have no rotation. So my configuration space for lambda says identity. Here it is. And then I go to the deformed configuration. That means I have some lambda for each point of the beam, different S. I have my lambda, which is oriented the cross section in the deformed configuration. Okay. And now in this cross section, acting the stresses. So in solid mechanics, this will be like a true Cauchy stress that sometimes you simply replace by Kirchhoff stress multiplying by J. We use that for plasticity, but they're still acting in deformed configuration. Hence, they have been parameterized by using the coordinates from the initial configuration. You need this position vector, which takes you from the initial to the deformed configuration. And then here on beams also, instead of just stress, this is either Cauchy or Kirchhoff, you need actually the stress resultants. And that's what I call N and M, okay? Maybe in shells, I was doing a little bit better job with the notation, so I could have also done this, didn't really explain in detail, too bad, but here it is, up, zoom, and then stop share, and then up share. Let's go into shells, here it is. So this is my initial configuration of the shell, where I have my position vector and like a curvilinear surface, as opposed to the body. And then I have a motion, which is phi of x. It could be something like a curvilinear path. And I get this particle at x, now at x phi. And the whole configuration A becomes A phi as a collection of the particle new position. So on this one, if I take a part of the shell, first I apply the applied loading, which I called here P phi and N phi. This is the same as this B phi, which is like a solid mechanics type of load that acting in the deformed configuration. And when I cut here, I have to put the corresponding stresses to keep equilibrium. So if it was solid mechanics, I was putting sigmas. And instead of that, I'm in shells, so I'm putting my stress resultants for normal and shear forces, and I'm putting the moments, okay? So basically, these are done in the deformed configuration A index phi. So I have linear momentum, I have angular momentum. And now I can move this into the initial configuration, basically by playing, first of all, reparameterizing the loading. I say if this load is applied that I call phi, that means over the surface infinitesimal element in the deformed configuration, I can get corresponding value of this load when it's applied over the same element when it was in the initial configuration. And then this vector is called P without phi. That's precisely what I say here. So P phi times dA phi is the same as P without phi times dA, where dA was like initial position of this infinitesimal element on which P phi is acting. And the same thing goes with them. So this is really reparameterizing back to the initial configuration. And then also you can have this one, this is now nonsense formula, where I'm doing this the same with these resultants that are occurring because I cut a shell, a part of shell. So I had to put the corresponding stresses in the deformed configuration. As I said, these are resultants of the, let's say, the stresses acting in the deformed configuration, either of the stresses, sigma, or whatever it is. And basically, I'm pulling it back to the initial configuration. So it turns out if I go through this development, basically this is expressed here. This is like a first Euler Kirchhoff stress, which is giving me the same type of explanation to the Cauchy or true stress. And that's basically is like from that one I can say that these guys are I think for the beams I was doing it better for the beams. Let me do it here. when I had this, okay, when I had it here, so stop share and then share again, up. When I had here, I said, okay, what is the physical interpretation? So when I get through the detailed development, it turns out that these, because I start with this type of thing, first pillar kick of stress, so my stress resultant become computation of these type of stresses. This is like axial and shear forces, and these are bending moments. So, and they are really the same thing, they're acting in the form configuration, but they're pronounced in the initial configuration. And then I can do it also pulling it back to the initial configuration. I don't know if I don't remember if I've done it here, but in any case, this is the kind of thing that is done there. I mean, it's really the same thing that we've done already for large displacement, but now has to be adapted to the stress resultants. And turns out that because you had the second Euler Kirchhoff by pulling it to the initial configuration, the weak form, here you have a biot because from the initial to the form configuration is just rotation, because that's the hypothesis of this structure thing. So that's
yeah. I was curious because usually when we build this kind of model using the first Kirchhoff and the virtual displacement gradient, we call this Lagrangian or material description. And when you said it was special, it makes sense because actually the first Kirchhoff is just a scale down for the current area.
Yeah, but in any case, you know, the idea is like, you know, Lagrangian versus Eulerian. In the general setting, it means which coordinates you're using. And I'm indeed using Lagrangian formulation because I'm using always the coordinates in the initial configuration. There's no doubt about that. Because I have to go for large rotation, which is also path dependent. I have to go to plasticity damage, which is path dependent. So I have to know where I come from. That means whatever is described with respect to the coordinates that I put in the initial configuration. That's one thing. As opposed to fluids, I just care about water that goes through Paris, not floods. And River Seine is definitely not starting in Paris. The initial configuration is much farther away, but you only care whether Paris will be flooded or not. You know? So this is the form configuration, and that happens to be easy to treat because they take simple cosine equation. The true stress of the river flowing through Paris is proportional to the velocity gradient and with some kind of viscosity, and that's it. In solids, cosine to be much more complicated. You have to take into account the history and the way you come from. But still, you have both configuration, initial and deform. And basically, when you have like let's say this initial configuration, for example, you have a deform configuration, talk about Cauchy stress, which is function of x-phi coordinates on deform configuration. Already, if you switch to Kirchhoff stress, which is J times sigma phi, is basically talking about the material representation, which is with the object which are sitting in deform configuration. That's why you call this spatial as opposed to material. And this is not now related to coordinates. Coordinates are always Lagrangian, but the objects that you are using are not. Hence, when you have S, you take derivative, you just say S dot. That's the partial derivative of the second Euler Kirchhoff stress, will take time. If you take this Kirchhoff stress tau, which is J times sigma, you have to go into this pulling it back, taking time, pushing it forward and stuff like that. You have to have these rates. And that's the same thing in the beams. When I was discussing this stuff for the beams, I actually I appealed to these rates. Just a second to get it back. Where are the beams up here? And basically, this is here.
So all derivatives in the beams context have always a Q transposed before.
See, that becomes it. Basically, I have my virtual work is a lead derivative, which is hopefully explained somewhere before. Its lead derivative is where are you? It's here actually. Lead derivative is all these trains are in the cross section. So cross section rotating back to the initial configuration is through lambda inverse or lambda transpose. That's lambda inverse. Then I take variation, then I push it forward by lambda. And that's precisely what is being done with this type of translation. And that's why this is the objects are, but these objects are in the deformed configuration. This is your unit vector in the deformed configuration, and this is your position vector of neutral axis in the deformed configuration. But both of them a function of x. Recall we have xy equal to 5x. So we think of that, and this prime is derivative with respect to s sitting in the initial configuration. That's the subtlety. So it's always coordinates are there, but what object are you using, that depends about the sparsity of the things and whatever it is, and or what the hell, it's just to make it more interesting, or at least that's really the key point of these large deformation. There's nothing more. They are just like small deformation, only a little bit bigger. And then they bring this thing into consideration, whatever. Okay, hopefully that settles, but we'll talk about that when you
Yeah,
hear a
yeah.
little bit more. So if it's not clear, that should be hopefully
No,
more
no,
clear. Okay,
no, it is clear. It's just sometimes I've seen
to settle in, to change your
the
vocabulary. Yeah, you had
yeah,
you had wrong vocabulary. Paulo is not very
yeah.
precise. You know, he taught you wrong language. No, I'm
No,
joking.
it's not.
Don't say
It's
that.
from before, I think.
Yeah, don't say
I
that.
think
Paulo is
it's
excellent. I'm joking. Paulo is excellent.
yeah, I
Otherwise,
know, I know.
we would not be collaborating. That's for sure. Okay. Any other question or comment or? Okay. Well, we
No,
are
that's
like
it. Thank you.
10, 10:33, and then let's say plus 15, 45, 48. Okay. 10:48, we come back. Okay, guys. Bon appetit or whatever. Bon coffee. So, okay, let us carry on. I wanted to see what I can actually do for this one, because we have covered, I would say, most of the stuff that I wanted to cover in a detailed way, and we started now this diverse applications, which are not necessarily the mainstream for each or every one of you. So I try to make a course organized in a way where what I really care about, that you absorb all these things. And I would say that the first four chapter, a little bit of fifth of the book, is the one kind of core knowledge that I want you to learn all, because this will be useful no matter what is your thesis topic. Tomorrow, if you're going to be working as a specialist with a doctoral degree, it's not necessarily going to be keep working on the thing that you've done for your doctoral thesis. That's actually what not expect. You could see that in my scientific career, I had to switch domain at least 4 different countries, 5 different universities. So you switch more than once. And whatever you're going to be doing in your scientific career, going from place to place or country to job, basically, you really have to kind of learn, because doctoral degree is not about what you specialize in one domain. It's about mindset that you're able to carry out very deep research and understanding of something which is not given to everybody, and you to kind of build your muscle that you can kind of deal with these things, and then they expect from you to come up with the new technology and things like that. And supposedly this is really the kind of the main goal of the whole story. So there's a core knowledge that I said there, and then different illustrations that we've done a little bit, maybe too fast today, but what can you do? So I covered everything that I wanted to cover in kind of solid mechanics. So let me then see what I would like to do in this particular point. And just a second here. Okay, I think I can do that. So I wanted to look into a little bit this in a very would say sujet d'actualité. This is currently a very hot topic, and that is like artificial intelligence type of story, because they are saying that many things will be changed because of this big push for artificial intelligence. So here I gave a recent lecture that I said, if you have a core knowledge of building this refined model with the reasoning of engineer, that upfront you make reduction of these models, and structural mechanics is a typical example of this kind, where basically on the hypothesis that your beam is slender and the cross-section is deforming certain way, or your plate or shell is slender and the fiber is deforming certain way, you're already significantly reducing the type of problem that you have to look at, and you can get computation results much faster, and basically with the knowledge that you put into these things. And contrary to that, what is called reduced modeling, I'll comment on that. Often, if you look into that very closely, it's really use of statistics. So today we live in the world of these social networks. You have your WhatsApps, you have your Vibers, you have your Twitters, or whatever now called X. And basically you have lots of information coming, and you have certainly been contacted on your mobile phones or on your fixed phones, whatever you have, and with many people selling something or pushing something. And often they try to engage you and get opinion on your side or something. And even if you use some of these websites like Facebook, whatever, Instagram, and the stuff, the product is you. You are actually giving information by yourself. And they use this information to take like a statistical average of the population. So I'm not much expert on probability. Whenever I work on probability, I work with two colleagues who are really top experts. One is a professor in Germany, Professor Mamatis, and then another one is Professor Tutsi, Professor Nicolas Limnios. They have really very complementary knowledge of the probability, and I work with one with the other to learn the stuff. But what I learned with them, they share the same thing, which is called the central limit theorem. When you have a very, very large distribution in statistics and probability, then the proper distribution is called the Gaussian distribution, which is characterized by the average value and the standard deviation. And then you can kind of decide something in a nice way. In other words, when you have like millions of people giving opinion, then there's a kind of tendency that the Gaussian distribution should be the best way to deal with this. because, you know, you can take the average of these millions of people and get something which is kind of meaningful simply by taking the average, and then you can see how many are very clever, how many are very, not to say jerks, and then basically what is the standard deviation, how can you get surprised if somebody is too good and somebody is too bad. Now, if you have events which are not so often appearing, then the key problem is really the probability distribution. And in fact, when you had the crisis in 2008, it was first one that shook Europe. That was actually the crisis of the market of what you call it, the apartments and houses in US, where people are getting a better and better house with more and more credit, which was basically not justified to give to people who have no potential returning the money. At a certain point, something went wrong, and people realized that some of these guys will never return the money. And then the property value started going down, and people started panicking. So nobody really understood how much the panic would actually perturb the whole market. And there was a crisis in the world that first time shook Euro. If you remember this, there was Greece was supposed to go out and was saved, and so on and so forth. I think nowadays there's discussion in US again. There was like you know, I had a recent experience teaching different places throughout Europe, and nobody is really willing to pay big money. Yeah, I used to be a student at Berkeley. As a foreign student, I was paying $6,000 a year. Now, and resident of California was something like a $200 to study there. So people, if they're Americans, they would spend 1 year in California to be able to pay 200 rather than 6,000. But now, whether you're California, whether you're American, you're a foreigner, the fees at Berkeley are $50,000 a year. And at Stanford, it's $100,000 a year. So nobody wants to pay this kind of money. And somehow, you know, in Europe, people have a tendency to think that the creation for free, but it's really not for free. These people cost a lot of money anyway. So the idea is really like as you build along, this kind of specialty knowledge is a kind of worthy, and you'll distinguish people who have this specialty and those who don't. And then if you really want system to be robust, God knows what would be next. For example, they're talking about, there was I think Biden was coming with this idea to forgive the tuition fees to people, because there are people who finish the degree in US, but the degree was no big deal and they cannot get the job. Now they cannot return the money that they had to borrow to fund their education. So it could be like next crisis anyway. But anyway, whatever this extreme event, also we're not about this politics or whatever money, talk about science. If you have something really like a special, then it becomes really knowledge of engineer, especially group of engineers. My philosophy now, you have to find colleagues with whom you can collaborate, and preferably colleagues who have complementary knowledge to yours. There's no point working with people who have the same knowledge as you, because you end up arguing, you know, who is right, who is wrong, but people are complementary, willing to work with that, and then you can start studying some really more complicated problem, you can learn something. In that case, if you're really studying something special, you really have to bring the knowledge up front, and then start to have probability to teach you a little bit. So this is kind of the message of this type of thing that I'm trying to leave you with as a message. In the process, I also want to show you there's a new book that you might be interested, not only this textbook. And as far as I know, it's not yet at UTC, but it can be. So I wanted to comment, what is this artificial intelligence in a nutshell? For example, in the domain of mechanics, this is called something proper orthogonal decomposition as a reduced model. And it comes from the studying the turbulence in fluid mechanics, where they were getting different type of pictures, different responses, and getting the average response, and getting how far each and every response is different than the average response, to master the turbulence. And in fluid mechanics, you know, I talked to many experts. They say the turbulence is never-ending story. It's never been solved. It's just like, you know, instability or fracture in mechanics. It's also a never-ending story. It's never been stored. So people doing homogenization, they have their own structural engineering, reduced all the modeling, and then they have to go along. So I wanted to comment on this in terms of a classical versus stochastic homogenization, because the classical view on homogenization was deterministic, but maybe the proper view of homogenization should be stochastic. And then also that how this can be used to explain what is really important, that is the size effect. Namely, people believe in testing, unless you test the real component that you're interested in, with the real size, the real material, with the real loading, your result, even though it's reliable in terms of test, might not be reliable in terms of the real life. because if your structure is twice or three times as big as your specimen, and it's built on composite material, there's something called size effect, that the failure modes might not necessarily be the same as the failure modes of this small specimen, simply because the heterogeneity in the large structure might be much more, let's say, important, and then the fracture being sensitive to the initial or induced defects, you start fracture sooner. So the bigger the structure, the more likely it is that you have a fracture sooner. And that's certainly not good news, because testing then does not give you the safety, but you still say on the side, which is not basically called safety. And then you can also go into dynamics and see this dynamic scale effect that I also to want to comment on, and then basically you can go into the studying instability, which really we haven't studied too much. Otherwise, showing you this examples with let's say this shallow truss and instability for a very simple case, but you can build the same thing in terms of something called less heterogeneous structures and so on. So, and then basically give you the conclusion about what is, let's say, the ratio between artificial versus natural intelligence, and if all these guys predicting that everybody is going to be swept away by artificial intelligence are right or not. So basically, that was just introduction. I already said that I had the pleasure of working in what they call the best laboratory for 15 years, and then decided to move to Saclay. This project started in 2014, 2023, as far as I know. Ecole Polytechnique is still not part of Saclay 10 years later. I might have not been wrong. So at the same time, Sorbonne and Pierre-Marie Curie was supposed to get in. We are now Alliance, so hopefully we're going to be getting there. So I asked myself, did I do right? Because initially, this is the Shanghai ranking. That's the reason why in France, the university starting getting together in this larger size institution, because they said, well, China being so large, they never noticed that France had very good education. And we are supposedly to be the third place in the world. And we have like 4 universities in top 100. And basically that university, Paris-Saclay, the one that I left, was to be the first. But that was at that time. And basically, they actually then refined the stuff. They realized that University Paris-Saclay is not the same thing as École Polytechnique, because École Polytechnique and Paris-Saclay are on the same plateau, but they are 5 kilometers apart, but École Polytechnique is still separate. So then Sorbonne University, where we joined, jumped over Paris-Saclay and École Polytechnique, which is a very small school, but supposedly very prestigious, went up. So it really, the question is like, whether you do right or wrong or whatever, but it's even the excellence, I would say, is really depends on let's say on a particular topic. And here I was visiting recently India, and so when I was there, I was reading local papers, and they're also obsessed with excellence like everybody else. So they say India is now number 4, and basically they actually, if you look into excellence, they want to also develop a STEM. This is science, technology, engineering, mathematics. And basically, IIT Delhi is certainly one of the best schools that I was visiting. But it's not only the whole IIT Delhi, it's actually the more like electrical engineering. They claim to be excellent. So it's really go finer and finer. At the end, excellence is at the local level. And if you really want to get excellence, then you have to collaborate with the proper people. And as I said, try to get the creative pairs, at least to have somebody who's willing to work with you and develop some kind of new theories that you can enhance your knowledge and this person can enhance his knowledge. And then you can kind of bring things further with the combined knowledge, because many of these problems are so complex today that a single person, either you spend the whole life studying different domains, or you learn how to work with others who have this knowledge and basically try to get this jointly under control. So after this long introduction, let me go into the core of the stuff that talking about what is this reduced order modeling and why do we need it. Here's this illustration. Basically, I mean, the performance switches I was working in, there was a nuclear industry with this, getting the safety of this nuclear power plants, in particular this protection structure, which is way too large. As far as I know, there's only one significant experiment. It was a Sandia experiment, which is 1/4 of the real size. Then competition between Boeing and Airbus is certainly important compared to developing airplanes in composites. And then basically the largest airplane in Boeing business was this 787 Dreamliner. So Airbus is developing similar airplanes, and you had to deal how to build this correctly. And basically, you cannot do the testing because what they call Toulouse test is a static test of a wing which is as big as 32 meters long and 6 meters wide, and you do statics. So this is not the same size that you really want, and nor is the same loading, because basically loading is a typical flat instability where you might have damage of these structures. And then you understand what you really tested and what is reality. And you have to do this. And so there was a aerospace industry a long time ago, was 2011. I was in this French Congress of Computational Mechanics, where a guy from this Airbus company was talking about pyramid of testing. With that time, there was like lots of testing at the bigger the better, the full scale. And then they wanted now to replace this with lots of testing on the small scale, and then do computation with the multi-scale computation to go up. But what he didn't explain is when you go into the very large size, basically you have this size effect, and you have to have this proper interpretation of the size effect to get a reduction of let's say, failure load due to the large size. Similar thing is for this energy transition. France has a really large potential, both of inland turbines, because lots of agricultural land where you can use it very usefully in way to power the electrical engines that go in to do the heavy work instead of the people, because you harder and harder to find people who want to do the agriculture. And then also for the competitive business, you need a kind of machines that don't cost too much money, that don't go on strike, as opposed to people who cost more money and they go on strike or they get sick, whatever. So the idea is like you have to have the energy to pump up this machine, or the other potentials along the coast. Both we have a big project with the Professor Pimenta from University of Sao Paulo, and basically it's about modeling these wind turbines business, because both Brazil and France have a very long coast. You can have these offshore wind turbines that don't bother anybody. And again, if you want to have a like really large production, need the blades which are 100 meters long, you can no longer test it. So basically the idea is like I already mentioned this, the challenge of this size effect is one challenge, the other is the predicting heterogeneous multi-scale model. So basically the durability of these structures, which are cement-based composites, you have to connect the scales which are of the order 10 to the power 3, and the scale which are of the order 10 to the minus 6, which is the level micron. Why this one? Because this is the product of cement hydration, giving you microstructure of cement, and then durability of a structure depends on this microstructure, because some of these components of cement are being damaged faster than the others. You have called lixiviation, sort of calcification, just like in osteoporosis, the bones of the old people. And basically this would lead to the fact that this structure is no longer viable. You have to replace it. There were already several well-known disasters with the bridges coming down in Italy, Germany, and so on and so forth. So kind of serious countries, and obviously nobody's. And then also the dams breaking recently in Libya and so on and so forth because of the durability issues. So the reduced order modeling, now you want to be able to estimate let's say the safety of some complex problem, or very quickly grasp to have some kind of initial design and things like that, is a very serious business. And many people who are mostly mathematics and whatever mechanics, computational people are trying to do this reduced order modeling. So what this reduced order modeling is this is compiled with the sources Herman Matisse, who goes often to these meetings. They do it almost every 6 months. I was there in something called the MORT 2019, joking with Professor Andres, who organized. They said MORT is like that. My God, not a good name, but this means model order reduction technology. So basically, that you have like a very big size model. It costs you too much, so you have to kind of do. So it's really like a multi-scale type of idea, but with a specific goal, and what to preserve, not to preserve. And so many works are done recently and published in this very active domain, lots of papers and lots of books, multi-author books. Typically, you don't find many of these textbooks, because really the knowledge, again, the core knowledge is about statistics. And these people are not expert on statistics. They illustrate through the application they're concerned with. And basically, the idea is that most of these guys never really considered fracture or rupture. And the only exception was the late Ted Belichko, who was really good in modeling. So he was doing this mesh coarsening to kind of go from fine scale to large scale when you have a crack that is propagating, and he always very good in bringing this crazy names, and one that he did multi-scale aggregating discontinuity called the MAD. You know, this was the idea. So how they build these things, this is a kind of in a nutshell. If you have model superposition, you compute your vibration mode by the stiffness matrix and mass matrix. And basically, then you use your modes to solve the what you call a model equation that are uncoupled, and you build any response by using certain number of modes, and you can reduce the computation effort in dynamics. Now, they might be dealing not with linear dynamics where the stiffness is constant, but something is changing. So instead of going for these eigenmodes, they go for these statistical modes. Namely, they compute the response for a certain number of time steps, for 1, 2, 3, and 4. At first, it came from fluids, and you deal with the turbulence. So you have, I don't know, 100 of these vectors that the size of 1,000. And then you take average of all these 100 vectors, and then you subtract each vector with respect to average. Then you have a matrix. You multiply this matrix transpose with the same matrix, a so-called covariance matrix. And then you build, let's say, the modes of such a covariance matrix, and then you truncate. So basically, your modes are no longer free vibration modes, they're statistical modes. So if you want to simplify to dynamics, you might be producing this response for some really, like you have a cantilever beam, and you apply force at the end, and the response that you compute will be dominated by the higher order modes. But then if you take this truncated basis for some kind of loading which wakes up higher order modes, then your response that you use will be kind of not very good, or the other way around if you compute it. So the fact that the loading enters, that you have nonlinearity, it makes this a little bit shady, unless you have a sufficient number of these representative. And it's always the question, how many do you need and whatnot. In other words, if you have a sufficient number, your distribution Gaussian, so you can be mastering the stuff. But if you don't have a Gaussian, you're in problem. So they say, okay, nonetheless, you know, that works only for the Gaussian. They are kind of optimistic, and they say that now ChatGPT, many people are using. Actually, but I told some people when you use it for finite element, it's not so useful because not many people talk to ChatGPT about finite element. But they say it's not going to replace only administrative people. We're going to replace chercheurs, ingénieurs, enseignants. That means researchers, engineers, teachers, and so on and so forth. And then you can kick out all. Well, maybe not, but the question is how to resist. What do we have to do at this stage? So the reason is I said, okay, well, you have the knowledge of the building reduced order modeling by engineering knowledge, and often it's called structural engineering. So this is a very recent book, just came out last year with Rosa Della-Mianava, who is my co-author. And we call this models and method for statics, instability, and elasticity, although we talk about dynamics at the end, but it's not mentioned because this is more traditional thing that people start with. So basically, the idea is that you need the structural models because they are not only useful for modeling at the macro scale, this, let's say, structures like beam plates and shells, or multi-body system with the slender components that are, again, looking like a beam plates and shells connecting to the joints. But they're also very useful for the micro scale. In other words, if I really represent these cohesive links and stuff like that, I already showed you that it's quite nicely represented by the Timoshenko beam. Not that I'm talking about Timoshenko beam, it's more illustration for the background people who are talking. It's really like dislocation, and the rotation is not only important, but you know, axial and do shear deformation is giving me the mode of fracture, which is mode 1, 2, and 3. And then rotation I can even neglect, but that gives you the tool how to model this. And we were quite successful modeling the fracture of complex composite materials like the cement-based composite. So the idea is like, why the hell write a new book when you already have these solid mechanics books? Well, basically, first of all, because building a model of solid mechanics and building a model of structural mechanics, you need some extra step because solid mechanics is kind of very simple. This is the message of all the course I was teaching. You have 3 equations, kinematic, constitutive, and equilibrium, and you keep turning it on and on. And they can go like whatever, nonlinear kinematics, nonlinear equilibrium, nonlinear constitutive equation. You have this fully under control. But in structures, you have very large diversity of the models because basically you can have thin beam, thick beam, thin plate, thick plate, this shell, that shell, whatever, this asymptotic developer for this. So it all depends what you want to do that. And I said initially, the historical knowledge of engineering was not using computers. And there was when I started my career, I went very quickly to the very high level of responsibility in this project because I was the one who could use these codes in a meaningful way, which all the engineers could not do that. And basically, that was really the kind of thing that was at that time, many people could do the simplify model upfront because they had lots of experience. Nowadays, people rely heavily on computer codes and they cannot build simplify models themselves. So I said with many experts who are able to build simplify models, structural mechanics, either retired or gone, nobody's there forever. You need a book to kind of preserve those. So that was really the main motivation. And then I wanted to write a book not only for PhD students, because the book I used for this course was really written for selfish reason, because I had always a very large number of PhD students when you have 10, and you want to spend time with people doing a third-year thesis, so you can do something creative and not spend all day just teaching first-year thesis, something. Then you need a book where people can learn themselves, and that's the point. You're doing thesis, you have to be able to learn yourself by reading books, because papers are often not easy to read. So a book is like transition phase between ability to learn how to deal with papers. But I wanted to write the book now, which is kept for a number of these level of students. So there's like, if you start at the bachelor's level, introduction is really to develop the core knowledge of the structural mechanics. So these are like so-called general theorems and methods of force and displacement that are predecessor, the previous method to the finite element method. So that illustrates on simple truss model everything you need to know. Then about refinement, reduction, which are fashionable words today. We are talking about beam models, the ability to build a meaningful beam model. So I discuss here we discuss here the model of Euler, Timoshenko, and Reisner, which is kind of the main reduced order modeling. So this will like bachelor's level. Then you move on to the master's level. For example, we studied the plate model, and one topic that I haven't discussed here is very very nicely representative for plate models. These are topics which are certainly the core knowledge of the using finite element model. That's called validation and verification. So what is validation? What's verification? Validation is the fact that you have chosen the right model. So with respect to your goal, what you want to represent, you want to find a sufficiently refined model with all the set of equations that are in to be able to get meaningful result. And then what's verification? Typically, the problem we want to solve is too complex to be solved analytically. So then we solve it numerically. And basically, you're talking about the density of the mesh, whether you actually have enough elements to be able to get the sufficient accuracy of your computation. So this has been illustrated for the question of plate theory, where we studied instead of the Euler-Bennu, we talk about Kirchhoff-Love plate. And instead of Timoshenko beam, you talk about Reisner-Mindlin plate. So one is thin, the other one is thick. Thin means you don't include shear deformation, thick means you do. And so basically validation becomes simply, in this illustration, whether the shear deformation will be included or not. And then you have a discrete Kirchhoff element, which is very popular element for thin plates. And very sure that the element which was possessed by the late John Argyris, actually, which was taking fifth order polynomial and the second derivative, which are curvatures, could be used for verification. It means each and every of these discrete Kirchhoff element could be validated whether it's sufficiently small, or you have to refine by using Argyris element in subsequent computation when you do this error estimates. And then also when you doing connection between the solids and the structures, you need to enhance the formulation of solids. This is what I presented to you yesterday quickly. These membrane elements with drilling rotation, with rotational degrees of freedom, so you can connect easily with structures. So this is actually also illustrated here. So I would say this is the knowledge that you already look into more serious master level. And then what is a number of topics dealing with when you're doing the PhD, this large displacement instability, buckling versus nonlinear instability. So buckling would be instability with small buckling displacement. So kinematics and cos theta might be linear, but the equilibrium is nonlinear. That's how Euler obtained his p squared EI divided by L squared. And then nonlinear stability, you have like a large pre-buckling displacement. So you have a kind of different situation that's certainly more difficult to solve such a problem. Then we have an inelasticity, but for structures, that you have an ultimate load computation of different type of constitutive model, plasticity and damage adapted to plates. and beams, and then we have localized failure, bringing it all the way down, all the way to also beams and so. And then I had to put one final chapter to give a glimpse of what is being done with the multi-scale dynamics and probability to kind of conclude on that one. So let me illustrate some of these things that are given in this book that had to deal with the classical stochastic homogenization, stochastic plasticity, dynamics, scale effect, and then instability of a heterogeneous solid beam. So what people do when they do homogenization, they first start by observing microstructure. Today, this is done either by digital image correlation, the way you glue the, let's say, a film on top of your microstructure, which is then deforming along with structure. You can post-process and get this displacement field, or you can do it if it's a sufficiently small specimen to put in X-ray machine. And you do X-ray tomography, you start a digital volume correlation, that means you have displacement field throughout the volume, and you can get a better match. And then you have these two homogenization methods, one coming from mathematics, the other one from engineering community. Asymptotic homogenization means that you are kind of expanding the fine scale equation into terms of some kind of powers, a small parameter epsilon. With mean field theory, you're choosing your representative volume element, and you're imposing the boundary condition that correspond to macro scale. That means you can either impose average strain or impose average stress to get either upper bound to lower bound, and then you go along with it. But these initial developments that were done in, let's say, at the end of 20th century, was basically geared towards elastic properties and not much studying the problem of fracture. So this is what is done here. Typical homogenization, as I said, you take the response to be expressed as a power of some kind of small parameter epsilon, although in many applications, not all, they never really explain what would be this small parameter epsilon. But if you do that and you plug it, this is like a heat equation type of thing, and basically you can get your average or homogenized conductivity coefficient by solving this problem for different powers of epsilon. And you have typical cell problems like a one periodic type of solution, and you get corresponding homogenized value of your conductivity. Now, in the representative volume element, the situation goes as follows. You can take a micro stresses as opposed to micro strains, and you can enforce either that the average of micro stresses is equal to some kind of macro stress, which is the one that is actually featuring this single point of your macro scale, or that micro strain is the average of the micro strain. And basically then it depends what kind of boundary condition you want to apply. Either you apply the say displacement boundary, this representative volume element, or you apply the stress boundary and this representative volume element, and this way you can get, in the first case, upper case, that means the upper bound or void bound, this is the stiffest possible response, where this would be lower bound or Roy's bound, this is the softest possible response. If you were to use a periodic boundary condition on this one, which is typical of linear elasticity, that means you keep repeating the same thing on two sides of the boundary, you turn out that you get the same result as asymptotic development. So basically, although these two methods are certainly based on rather different hypotheses, at the end they result with the same result. And that's kind of quite pleasant. Now, either of those things really, as I said, they never really defined this little epsilon, or they never really defined this size of this representative volume element. So if you really want to talk about that, the idea would be you can do stochastic homogenization, which is basically computing, let's say, the averages of your properties, and in the spirit of the multi-scale modeling. In particular, this becomes something like a goal-oriented type of multi-scale modeling. In other words, you have to set your goal. Your goal should be, let's say, a quantity of interest, which is expressed here as y index n. And basically, then if you have a microscale, that means that you can see all the fine details that you might be interested in. You can run this computation by using finite element models. So inside you have plasticity, damage, fracture, whatever you want to put in there. And then you have to put a corresponding macroscale model, the one that you're trying to be a representative but reduced size. And then again, this model should have access to the same quantity of interest. So for example, for the finite element and homogenization, it is already used, is basically you're talking about internal energy. And finite element model is discretization method, which gives you the best approximation property in terms of internal energy. And then if you talk about the dissipated internal energy, that's called dissipation, you can extend this validity that this is best discrete approximation for the something like plasticity damage and so on and so forth, which is already not so bad. And so basically, if I take this in the spirit of classical homogenization, that means I'm getting energy in terms of both of these models, so dissipated energy in terms of these both models, then I can characterize behavior of the macro scale model by the parameters, which are not necessarily deterministic, but they could be random variables, as opposed to this microscale type of parameters, which are random fields. So homogenization already reduce random fields to random variables, random fields being both function of the coordinate and the probability variable omega, whereas random variables are just function of the probability variable omega. And they have done the same type of work like homogenization, but in the statistical manner. And that's actually what is done there. So how it is done, this is today done by identification. So identification is actually quite ill-posed problem. Typical identification follows. You're solving your problem. Typical thing is you apply the loading and you obtain displacement and strain and stresses. This will be forward problem. But in the inverse problem, what you do, you apply your loading and you measure displacement, eventually measure strain, and you try to understand what are the parameters of your constitutive behavior, for example, or other type of parameters it could be that you're trying to identify, so that the results that you measured should fit the type of behavior that you will be predicting with this particular model. So basically, this is ill-posed problem because it turns out that many different parameters can fit into that, and you have to do regularization and so on and so forth. So this is there are books about inverse problems, how to do it. Now you can turn this ill-conditioned inverse problem into something which is well posed if you appeal to something called Bayesian inference. That is, you now place this mechanics problem inside the probability space, and the parameters, they are no longer considered deterministic, but they are like random variables. You actually try to establish the distribution of these variables that could be parameter of a problem. For example, Young's modulus, yield stress, and so on and so forth. So basically, if this distribution is Gaussian, but it's not often Gaussian, you can imagine by the probability distribution defined by the average value. So this is just like deterministic value. And then on top of that, you get standard deviation. It means how much you're wrong. It will be 10% below, 10% above. It depends what is the standard deviation. Let's say it's 10%. So basically, the way it goes is the following. First, you ask for a forecast. You ask some expert, what do you think about would be the best approximation for that type of thing. Actually, I was talking about this crisis 2008. I remember after this, I was reading about one guy going around the genes, and he built a kind of course that is teaching this people working for the banks about what kind of probability distribution they should be using, because as much as you can have sophisticated equation about propagation of uncertainty, if your probability distribution of those things that start with is not sufficiently credible, then the probability will not give you a good result, that's for sure. So really, then he was teaching people in business banking how to get a good probability distribution, so to make sense out of these probability measures. So collaboration with my colleagues, Matisse and Linus, I try to provide the probability distribution of these things that go on the micro scale, and they come up with the probability stuff, and we kind of see at the end what is going out of this in terms of the estimates. So basically, once you have this forecast, the probability distribution, then you have this new observation. In other words, you run this type of thing, and then you improve the probability distribution with this measurement, and you get some kind of assimilated probability distribution, which is supposedly better than what you had before. And basically, this is done by using representing the probability space in terms of the, you can have a transformation that express the probability, let's say, variable you're trying to identify in terms of these Gaussian uncorrelated variables. So if they're Gaussian, basically they could be completely independent if they're uncorrelated. So basically then they become something like a Cartesian coordinates in the probability space. Only the Cartesian coordinates you have 3. In probability you can have as many as you want. So the problem is there that when you have as many as you want, you have curse of dimensionality, and you end up having to identify many, many different type of things. So it's always a good idea, like when I showed you roughly how we try to identify the damage model parameters. If you can split it in the block of these parameters, initially you consider some of them deterministic, and you take the measurements which are only pertinent to those that you try to identify, and so on and so forth. So they kind of reduce the size of your problem that in terms of identification. this is always a good strategy. And only at the end, you try to build all of them at once to see if you are really fitting correctly. Now, going through this procedure, you can have two types of different approaches. One is called Markov chain Monte Carlo, that's more close to Linus, and the other one is called Gauss Markov Kalman filter, closer to what is the favorite approach of Hermann Matisse. So in this Markov chain Monte Carlo, what you're doing, you're every time updating the probability measure, and you keep the same approximation of these parameters as in terms of random variable. As opposed to this filtering approach, you are basically you are not updating probability, you keep the same one, but you just update the function. In other words, you take this to be a combination of these Gaussian variables, so the probability measure is already there, and you simply say, okay, what is the nonlinear function Q, a function of these Gaussian variables, and you're in the business. So basically, when you run this, we tried both. One was done in terms of identifying something like inelastic behavior and things like this, where we're running this filter approach. And then the other one was instability of heterogeneous solid beam. We're running this, let's say, Markov chain type of Monte Carlo there. And basically, if I go to the first one back, if you have identification of the elastic parameters, you realize it's quite fine to do homogenization, kind of converge. You can even take like a predictor to be the previous step and accelerate this type of convergence, which normally you should not do. You should keep the same predictor and do this type of thing properly. But in homogenization, it's so easy that it works without any problem. But if you go into the localized fluctuation failure, definitely this is the final distribution. So definitely, if you start with Gaussian, definitely not go through, because it can be sensitive to the initial effects, and then you can get something which is certainly a better estimate of the particular instability. So the kind of multi-scale analysis is really like a goal dependent. In other words, you really have to say what is the level of observation that I want to go with refine, and what is the level of this reduced modeling that could be used to get the proper result, and kind of start it from there. So here's the illustration we are doing. For example, you start with the fine scale, where you can see the random description of this microstructure, something like a cement-based composites, and they are like either aggregate and cement that are put together with this cohesive links. And then the parameters of failure, given that this cohesive links are represented with Timoshenko beam, you can have mode 1, mode 2, mode 3, and these parameters are described as random fields. So the goal of our reduction is to describe this to be with random variable. So first of all, show that you can do it this in the elastic process. You can do this fully multi-scale analysis, no problem with the concrete representative 3D material. You have to do these links that are properly treated with getting the, let's say, correct representation of the strain field with the jumps of the strain field along with the jumps in the displacement field to a localized fracture. Jumps in the strain field is needed when you have a link like that, which is somewhat in aggregate, somewhat in cement biased, and basically you can have it here. This does the same job as XPAN, but only better in the sense that this is an enhancement of your total strain, and this is your generalized plastic strain. So this type of model really gives you excellent results for a tension test. You cannot do this other than numerically. Gives you isotropy, statistical isotropy of concrete, and give you the ratio of 10 times in compression larger than tension, biaxial compression, and so on and so forth. And then if you now build a macro scale model, you have to be able to reproduce many of these salient behavior that you observe at the fine scale model. Of course, you cannot, if you go down the way to localized failure, you'll need to have a discontinuity. But typically, let's say you're going to be developing a node solid element, which has this discontinuity. Now, this is the real discontinuity. Typically, the cohesive links that are at the interface with aggregate and cement are breaking, and this surface is anywhere from different than plane. So you can never really represent the whole surface this way. It will be just too hassle, too much of diversity. So just take a plane, but you make sure that the dissipation that goes into breaking all these links and dissipation that goes into macro scale model are the quantity of interest that you're running, and they're forced to become the same. So first of all, you need like a macro scale model which has all kind of possibility of the different failure modes. So for that one, we take into account like something failure in shear, which is a Drucker-Prager mode, and then something that is failure in tension, eventually in compression, and this is spelled out with Saint-Venant criteria. So this becomes your multi-surface plasticity model. We combine Saint-Venant and Drucker-Prager, and you end up having a number of these parameters. This is a bulk modulus and shear modulus to quantify the elastic response. Then you have the tensile strength, the compressive strength, you have a fracture and tension, fracture and compression, and so on and so forth. So we built such a model, and the goal would be now to go from the reduction where everybody, the fine scale is considered to be a random field, to the scale at the macro level where these are simply random variable. And so this is what has been done. You have your computation, the fine scale. This is your really refined model where you can see the difference between one part of the domain, which is aggregate versus cement, and the true representation of failure modes, typically at the interface, and the true representation of your fracture surface. And now you say, okay, I cannot represent that. I simply have my plane, which is discontinuity plane, giving you this embedded discontinuity for this particular hexahedral element. And then basically, I want to make sure that the energy that is dissipated in this microscale model is matched by the energy that is dissipated in this macroscale model. And that's the way it is done. And then basically, I can show that in the elastic parameter, you go very quickly. Then the stochastic, let's say, homogenization for the hardening parameters can also be done. And then for the softening, you have more troubles, but then typically you still have some homogenization. And you can say that the error that you can tolerate has to be bigger and bigger if you go down to homogenization. So at least you get some estimate, you get your bounds, which are certainly larger when you're trying to estimate this, but you definitely have a, let's say, a more efficient approach with this type of thing. So now this was just homogenization done in stochastic. If I now want to be able to deal with the size effect, and that was the idea of this first suggested by Bajant with this 3-point bending test, where he said that for some kind of small specimen, this is breaking like continuum mechanics, and for large specimen, breaking like linear fracture mechanics, without really ever, as far as I know, explaining what do you call about large or small. Because here, for me, there was different failure modes. You can have failure mode in bending, you can have failure mode in shear. So definitely it's not the same type of thing. So I said there was one difficulty to deal with, which is the proper formulation of this thing, that is basically you take into account that you can have for massive structures, two types of dissipation. You can have a volume dissipation, you can have a surface dissipation, and then basically you have to connect these two, and then you have to have a proper representation of kinematic field to handle this mesh of reactivity. So all is said and done. Let's say you run now the computation to explain the size effect. So this is your specimen done in 2D. The green things is an aggregate. It's done in terms of the, let's say this aggregate curve, either full or empire, you know, how many big and how many small we put, only you don't know where they're going to end up. So we do this in Poisson process rather not to overlap. It becomes Gibbs process, and you fill in the domain with this corresponding aggregate, and then you run computation, assuming that the limit of elasticity will be when you have first plastification of the cement, and it took it elastic, perfectly plastic, and after that it spreads and has percolation. So the ultimate we stop when you have a percolation, when you go plasticity from one end to another. And then basically, now the results that are different realization given here, you can homogenize. That means your properties are constant throughout this element, or they can be a random variable, or if you really want to have a size effect, they have to become a random field. And basically this random field, now we estimated this random field for yield stress and for the ultimate stress, or rather difference between ultimate stress and yield stress, so that becomes always positive to make sure that ultimate stress is bigger than yield. And basically, this is represented so-called isotropic random field with something quantifies the correlation length. So correlation length is distance which you have to travel where the properties are likely to be similar with the variance sufficiently close. So you can say this is a homogeneous. And then you can run this computation with a small specimen. That means it's the same as correlation length, 10 times bigger, 100 times bigger. So the bigger it is, the more variability you have. If it's small, it's kind of almost homogeneous. And then the bigger it is, it breaks faster. and the contribution of the fracture process zone becomes smaller and smaller. And that really gives you the option to say that you can master the size effect in terms of something which is the true representation of a microstructure, and the estimate of correlation length to say how, let's say, homogeneity of the structure should be justified or not. So if you have now the same thing in dynamics, for example, something like earthquakes and stuff, which is still the biggest cause of human casualties, in the recent examples are piling up. First of all, you can build your reduced order modeling. This was one part of my collaboration with Ed Wilson. Papers we wrote, even now in this computer code software SAP, which is marketed by computer company CSI, I think Computer Instruction Incorporated. You can see, you know, $10,000 you could buy that without any problem. People, lots of them bought. And the reason for that, you can rent out, this is a computation that was done in Dubai. I know they have offices in New York and in Dubai, and also in near California. It used to be Berkeley, now it's Walnut Creek, because I guess the owner lives in Walnut Creek. And the idea is that basically you can have the really with the rich vectors, which are kind of a clever combination of eigenmodes and something called static correction. We have this in this paper here. If you're interested, those who are doing that, I can give you those. But the idea is like you can reduce from half an hour, this is in seconds, close to 1,800 seconds, to something like a fraction of 5 seconds, 7 seconds, and so on, and have really very good response. And then having to do a much more refined modeling in dynamics, of course, you have to build a very refined stuff. And basically, for example, the typical result would be measuring of the structure. So this is coming from this ESSA laboratory, which is part of the European Union in Ispra, small village near the border between Switzerland and Italy. So what they do, this is typical villa in Greece, like a 2-story building that people who can afford buy. And then having lots of earthquakes there, they reproduce something called pseudodynamic testing. So they can actually go the computation of the response, they can compute acceleration, and then from that one, they predict what will be the corresponding displacement to get internal force. Then they put this motion with the hydraulic these devices to pull it, and if you accelerate, you see these people are moving very fast, but in the reality, they don't move so fast. They take a coffee and stuff like that. It starts really looking like realistic. So then you're really measuring the response of your structure, and you're trying to fit this in the proper way. So obviously, you know, you realize that the dumping is much more complicated than what Rayleigh can give you, and we discussed this. You can have phase 1, phase 2, and so this way I can, if I have a really dumping, this is actually this type of famous result. You have it in book called Clough and Penzi in many other places. If it's dumping proportional to the stiffness, it goes up linearly. If it's proportional to mass, it goes down basically as this exponentially. And then typically you choose your dumping ratio for certain interval of frequencies. And even those values, you have the dumping you want, but not necessarily in between, or certainly not outside. So you can never really reproduce what you really need in terms of shaking, unless you go for this more refined modeling. And the very kind of, what is really good, you get this exponential decay. So if you want to get a refined modeling with plasticity, so you don't have it, this is the kind of thing we discuss. You have all these type of results. And basically you have your evaluation. I presented this in detail. And then basically, if you have a viscous damping, you have your exponential decay. But if you have a frictional damping, you have your linear decay. This is coming from a classical work of Inman in his book. But basically, you can actually get those two match if you take into account heterogeneity. And especially with lots of heterogeneity, that means there's large standard deviation of something like cold yield stress, that starts looking like exponential decay. And basically, the moral of this story is that you can identify behavior that explains dumping at the material scale. And then with the measure of, let's say, heterogeneity of structure, you can get it interpretation for particular structure. So something which is homogeneous, something which is heterogeneous is not going to have the same dissipation. So identifying the Rayleigh dumping, you have to repeat the test with the every time with the new stiffness, new mass, with the real structure, where see you do the test on the material level, and then you interpolate that in terms of the computation. There's also the point of when you're doing the computational instability. Now I haven't discussed this in detail. You have it in chapter 8 in the beginning. This is one part that I never touched, but I can do it now. Basically, when you have instability with, let's say, large pre-buckling displacement, the condition is always the same. Your matrix tangent stiffness matrix becoming singular. Your lambda, the eigenvalue that correspond to this one becomes equal to 0. And then psi here is your corresponding critical mode. And so if you want to obtain exactly the result when you get these critical points, these are the points where the small perturbation load will lead to the very large disproportional type of response with a large displacement, large rotation, so on and so forth. You can then make analysis which shows how to distinguish between limit point being the point where you can no longer climb, that's the ultimate resistance to the structure, and something called bifurcation problem, where typically structure snaps from one shape to another. And so basically the first one is computed when say you're getting the limit of your lambda, so L would be just the norm of this critical mode -1, or the bifurcation mode is computed when the critical mode is perpendicular to the loading that you're applying, because you snap out in different things. So it depends what you put here. In L, we have a quadratic convergence on the direct computational instability point. So when you have this direct computation, you have these stability points, then you can explore the whole set of the behavior. Now the same thing is done for the beam. So if I have a large deformation beam, this is in 2D. We just discussed this earlier. This is my initial configuration. It's a straight line aligned with the axis x1 with the vector e1. Then I have a large displacement and I have large rotation. So a1, which is still perpendicular to cross section, is not along the tangent. And a1 is computed as cosine theta e1 times sine theta e2, where theta is the angle of rotation from the initial to the deformed configuration. And then basically I can say my axial strain is this guy, a1 transpose phi prime minus a1 transpose e1, and then gamma is a2 transpose phi prime minus e2 transpose e1. So this happens to be equal to 0, this happens to be equal to 1. So from this I conclude that a1 transpose phi prime is equal to e plus 1, and a transpose phi prime is equal to gamma. And then I take a moment equivalent equation, I plug it what it is in the phi prime, and I get this equation. And then you can see from here how the Euler elastica would occur. First, you have something called Kirchhoff beam. When you simply kill the shear strain, you still have your axial strain. And some people were developing this recently for something like a very thin, slender structure. And you study something like a structure of the lungs or whatever. This I was recently expert in the thesis in Dublin, in Ireland. They're also developing this for modeling this type of wires with a different type of thin fibers put together. And basically this was also crucial beam, but what Euler was studying, he studied Euler elastica. That means you kill both gamma and you kill axial deformation, and you reduce it to this one. So this is your instability equation for the nonlinear rotation. So here we have a sine theta. But if you now reduce it to very small pre-buckling displacement, that sine theta will become the same as theta. So that becomes your Euler buckling for linear case. And you can say that the critical mode for this one would be equal to 2n minus 1 to the power 2p squared ei divided by 4l squared. 4l squared is actually 2l divided by 2. This is your buckling length. If you had a simple support width, it would be just l squared. And basically take the smallest value, which is then equal to 1, and then typically you go for that, and this is your critical mode. So large displacement would lead you to this equation. Small displacement would lead you to this equation. Now you can also say take a reduced modeling, and especially for non-conservative loading, which is the thesis of Rosa Della, basically you cannot reduce the static, you have to go for dynamics. What you're then considering is basically the vibration when you kind of have something critical load, you put it there and you give it a little push, like a small impulse, and you see how the vibrations are changing. And if you take a certain deformed configuration represented with some kind of, let's say, a shape, something like a Hermite polynomial for Euler-Bernoulli beam or something like that, you take them, and then you average. It turns out that you actually reduce this problem to something called Duffing equation, Duffing oscillator, which is a very famous oscillator for studying of instability or motion under this. So you can have something like you put damping so you can reduce it. So if you have a stable, these are your state space approach, displacement and velocities. You can have these circles with constant energy. And if you have dissipation, you can start reducing this energy and so on and so forth. Now, if you have instability, basically you have like 3 different configurations. These 2 points to the left or right, or one in the middle. and then you can run that. And then instead of running this under some kind of perturbation, which would be like a cosine omega t, you can run this with a white noise perturbation, and you can start consider the distributional probability for heterogeneous beam. So for the stable case and unstable case, and you can get the, let's say, the probability of the instability occurring there. So this is actually the stuff that, with different illustrations that we brought to in the last chapter, that are not necessarily, the most pedagogical, but just to give you the flavor of what is currently of interest and what you can do. So I illustrated a number of things with the idea that go all the way to the fracture model, where the reduced modeling has not been done successfully. So to give you some indication how you can build this fracture model using the probability, which is the main tool of this artificial intelligence, and also to give you something like an illustration of how you can capture and quantify the size effect, the scale effect, and stability of heterogeneous beams and things like that. So basically, what I said is the following is the conclusion. We would like to illustrate with this book, perhaps the best possible manner to combine the expertise in structural engineering with artificial intelligence skills, namely the model construction in terms of the best choice of hypothesis for given goal. One should have expertise in structural engineering, you or the whole group of people working with. And for model selection in terms of validation, verification, means whether the model is right, whether the sufficient discretization was done, then you can use the heuristic tools and the statistical method from artificial intelligence. But to put it the other way, if you start with a lousy model, probability will not give you a good model. You will have something called garbage in, garbage out. If you have a choice of several good models, probability can give you not this model is developed by this famous professor, that famous professor. Is actually what is the goal, what is the standard deviation, what is your, if your standard deviation is big, that means your model is not so good. Your standard deviation is small enough, your model is good enough. Often it's not really Gaussian, but what they are, this is just for the illustration. Some of these recent papers that are dealing with that are given here. And basically that is the one that is, so perspective whether natural and artificial intelligence, whether stochastic can fully replace modeling. I'm not really sure. I don't think so, because basically this statement, if you read all the way to the end, was given by 350 researchers in artificial intelligence. So every good researcher thinks that his or her domain is the best domain in the world. And if you don't think that you can do better than the other guys, you're not a good researcher. This is the first quality. So whether they're right or whether they're wrong, it's, the time will show. But definitely they have a big power of money, because these guys are coming from Google, Facebook, and the other companies that made a ton of money by using basically the knowledge of people and getting their statistics. So it's like I based the book lots on this one. I just give you a glimpse from that one, and please note that you have many other things that you want to consult next to these papers as we go along. And so basically, when I was publishing this book, we were advancing quite fast, especially during my summer vacation. I had more free time to work on that. But it's interesting, near the end of summer, on August 19th, I was approached by the people helping Springer. These are from India guys. And they asked me, thank you for interest in publishing with us. My name is Srutika Dasari. I support the editorial team with the Springer Nature Research Reading and creating machine-generated literature review. This is now complementary auto service that I would like to introduce to you, since it was very well received in pilot phase. So basically, this technology helps to auto-create data table contents with a list of rated readings. So what this person did, they took the papers that are published in Springer Journal, not all the papers, and they took the keywords and they compiled 150 pages with the table contents and the kind of stuff that basically is already like contents of some kind of, and it was really in one shot. I was sent 150 pages to look at it. Honestly, I was really quite shocked. And then I answered, basically this is it. I said, the guy here, Pier Paolo Riva, was the editor of Springer, and this is the person who contacted me with the tools from Springer using artificial intelligence to write a book. So I said, thank you for your offer, for helping me with artificial intelligence. But my book is precisely about opposite choice. Namely, I advocate that the first step should be an expert in structural engineering who chose the model and what to do, and then use artificial intelligence for model validation verification, or hear how good the book will be. In other words, I already tested this idea, and that's really true, not with everybody, but with top expert structural engineering. I had the pleasure to work with many of them from US, Germany, France, many other countries, and I send them parts of the book or the whole book in the first version, and I asked their opinion about that, and most of the time they said, okay, this is good, that you do this and do that, and then I can kind of do this. So basically, by compiling some kind of artificial intelligence statistical guys, all kind of gibberish is not necessarily the type of thing that in my mind is a stuff. So basically, the idea is that the guy who had it all, he said it like this, bring really the body issue, because the knowledge, how we kind of progress and we deal is we are challenged by the people we work with and colleagues who have certain knowledge complementary to yours. So this is one of the guys who actually built a very important algorithm in computer science. David Galanter has one of his algorithms to his name. And basically, he was one of the unfortunate guys. There was a certain guy called Bomber. I forgot now his last name. He was living in some kind of mountains, and he had some kind of grudge against the university professors. So he was sending the letters, and inside the explosives. So he was one of the victims when he opened that letter that exploded and then cut off his hand. So when you realize that you have a body injury, you realize, he said, I can build a application and run it on this one, but can I build an application and run it on somebody brain? Obviously, he said not. He said, we already have the most singular intelligence available for study, the one that produced Bach and Shakespeare, Jane Austen, Gandhi, and so on. And we scarcely understand it's working. So we blunder the head of ignorance and talk about replacing it. So basically, it's really like, the way I understand it is really a kind of, you have a really specialist or certain domain, they make the significant advances, and then the other guys are just following and doing interpolation, extrapolation. So basically, I was lucky to have many of these guys that I worked with, and then basically you reach this one. So I had this plaidoirie. This is Ed Wilson here, for example. This is Rubinstein, Professor Mang. This is Ladevez, Scheffler, and so on and so forth. This, my former student, is now Dean of Civil Engineering. Colleague Ivica Kožar there, Pavo Marovic, again Ivica Kožar and stuff like that. Boštjan Brankić, Professor, this is our course in Slovenia, Professor Jose Luis Perez, Louis Matis, and Professor Levi from Israel, Paulo Pimenta, and so on and so forth. There's difference, and then there are of course the contribution of different type of PhD students and stuff like that, Well, most of these guys are now professors, which is kind of pleasant anyway. So what the hell, who says we are not relaxing at the end, huh? Yeah. This is the Silence organization, 2018. We brought 300 Brazilians to Copiane. Best thesis award for some of these students and so on and so forth. This is the last meeting in Split. Recent pictures with the current students and collaborators and so on and so forth. So the biggest thing is really like how to deal with the other guys from civil, mechanical, and so on. And then if you don't, what the hell, you can still go to take your vacation. So roughly, this is what I wanted to say. So basically, what I suggested up is following. Tap, share screen. I send you all links for tomorrow's session because I'm busy. I cannot do it in person, but we are going to the level where there's so many diversity and stuff. So I suggested some of these readings, if you want, from my website for different topics, fluid structure interaction or resilience or other composite materials and whatnot. So these links will give you the type of thing that you might want to look at and complete there. So this is it. So then I'll send you also the connection to, we said 29 when we see each other for the final experience. I'll send you the passage of this morning session for evaluation of this critical review of the papers I send you. I said, I think I already got that. Yeshua, maybe you didn't tell me which one you want. Please do it so I can send you so you have enough time. And then we'll have like a small written exams, 1.5 hour for the theory part, 1.5 hour for the exercise part. This is really like the exercises I was giving you, drawing these little homeworks, and theory part will be just straightforward answers. So both of them can be handled in 1.5 hour if you study that. And then we'll complete that, and then hopefully this is the end of the experience. So I hope this will be at least mostly useful to you. If you have any questions or comments, feel free to contact me by email or any other way. If you can do it in person, and we can discuss from now to 29. Even after that you finish, if you have problems, I'll be glad to help you working with my colleagues or with me. So that's my obligation. There's no problem there. Okay, so that brings us to the noon lunchtime and the end of the course. So I can stop here.